This mighty metropolis stretches 1,600 square kilometers. It's one of the world's busiest cities, crammed with people. But danger lurks beneath the city streets. London's sewers have reached bursting point. The network's choked with wet wipes, nappies, sanitary towels, and fatbergs the size of football fields. Engineers tackle 5 blockages every hour. It's costing £1 million each month, and the torrent of raw sewage is overflowing. Archaeologist Cassie Newland is looking at the root of the problem.
London's original sewer system was built 150 years ago by Joseph Bazalgette. He was considered an engineering genius, but time and London has moved on. We've grown from a population of 2 million people to more than 9 million people. And the way we live here has changed. If you think about the land on which those skyscrapers are constructed, in the Victorian period there might have been a handful of terrace houses, maybe sharing 1 or 2 toilets, and now there are 95 floors and people sharing hundreds of toilets, and the system just can't cope.
For centuries, we've been struggling to deal with our most basic problem. Before the sewer was built, Londoners dumped their waste onto the street before being emptied into the Thames. The invention of the flush toilet bypassed the streets, so now people could dump their waste directly into the river. But as the Thames water was also for drinking and washing, it was only a matter of time before the filth became too much. During the hot summer of 1858, Parliament had to be suspended when what became known as the Great Stink outside had become a danger to health. Today, the mighty Thames is under threat once again. Living alongside the river, London-born construction engineer Ray Cantwell knows the extent of the problem.
My mum used to actually be able to swim across the River Thames from Bishop's Park over to Putney. It probably wasn't recommended back in the day, but ever since then it's getting worse and worse. It's horrible to see, horrible to work around. It's quite disgusting actually, if I'm honest with you.
London's original sewer was designed for both sewage and rainwater. The water carried the sewage away from the city. Following heavy rain, combined sewage and water overflows, CSOs, prevented sewage backing into people's homes by discharging directly into the Thames. The emergency CSOs were only designed to operate once or twice a year. But today, with more people and more rainfall, London's overwhelmed system discharges sewage almost every time it rains.
Whenever there's over 2 millimetres of rainfall in London, these CSOs release tonnes of untreated sewage into the River Thames, approximately 34 million tonnes on a typical year. Sometimes when you do have heavy rain the night before, you can come onto the site and actually see the amount of sewage going into the river and the complete discoloration of the River Thames, which is not a nice thing to work around, but definitely not a nice thing for the Londoners who want to use the river themselves. This is the main problem that we have to tackle.
Something has to be done to save the Thames. So engineers have started one of Europe's biggest construction projects. The London Super Sewer.
This is a huge undertaking in the centre of London. The scale is just enormous.
A multi-billion-pound feat of engineering extending London's sewer system.
This is exciting. This is the pinnacle of civil engineering. It's the mega projects that get the attention. That's really why I got into engineering.
Designed to transform the River Thames, it's truly groundbreaking.
Some of the things that we are doing here are cutting-edge technology, world-class engineering, so I'm pretty sure a lot of other countries will follow on from this and use this as a set standard.
I came from another major project, but this is next level.
The super sewer will bring the existing network into the 21st century. The combined sewer overflows, CSOs, will be connected to 24 deep shafts. Under the ground, 32 kilometers of tunnels will thread their way through the tangle of the city's subterranean infrastructure. At the deepest shaft ever dug in London, sewage will be pumped the height of Big Ben, up to the largest treatment works in Europe.
There are approximately 54 sewage outlet points across the River Thames. The Thames Tideway Tunnel project aims to intercept these worst offending CSOs, send them into our tunnels and our shaft down to Beckton sewage treatment works. In essence, once the project is completed, we hope to reduce the amount of untreated sewage that is released into the River Thames every year by about 96%.
But such an ambitious project is full of challenges.
How do you prevent millions of tons of toxic sewage flooding the Thames? How do you tunnel beneath London's underground rail network and the river itself? How do you pump thousands of litres of sewage vertically to the treatment plant? And given how dense London is, how do you manoeuvre the enormous equipment through such limited space?
Engineer Josh Roy is overseeing one of the first stages of construction, the drop shafts.
This is the viewing platform, which is the platform where the crane supervisor or the banksman coordinates lifting into the shaft, and effectively it's the only position you can see down into the drop shaft during construction. The internal diameter of the drop shaft when it's complete will be 15 metres, and currently we've excavated to approximately 12 metres below ground level, and we are continuing to 32 metres below ground level in total depth.
This is just one of 24 shafts along the river, some as wide as the dome of St Paul's Cathedral, engineered to tackle the biggest sewage overflows.
Crucially here, during a normal year, a number of overflow events occur, which means that pollution obviously goes straight into the Thames. So here we're providing a drop shaft, and in the future, a series of interception chambers will take any overflows directly into the tunnel rather than into the Thames.
By connecting the existing sewage overflows to vertical shafts, engineers can start to intercept the most offending CSOs. Buried underground and flooded with tons of sewage, much of the network will be inaccessible for servicing. To ensure it functions maintenance-free for decades to come, engineers must tackle a fundamental problem.
At this site in particular, beyond a depth of 4 metres, we are well past the groundwater level, and therefore we can expect to have some kind of water ingress as we construct, and that's one of the biggest challenges on this site and other sites across the project in London.
The shafts are reinforced with concrete, but over time they can be corroded by water outside and sewage within. Under the microscope, concrete is laced with tiny capillary channels. Water and sewage can permeate these capillaries, causing irreparable damage. Engineering a network to withstand sustained attack from water and sewage is one of the biggest challenges. Buried so far underground, this project must be engineered to last. To find long-term solutions, archaeologist Cassie Newland has travelled to the ancient city of Knossos on the Greek island of Crete to see a 4,000-year-old Minoan marvel.
This is Europe's oldest city, the London of its day. While we were busy dragging rocks around at Stonehenge, this was home to up to 100,000 people.
But sustaining so many people in this landscape wasn't easy.
So the great challenge of a city like this is getting enough fresh water for people to drink. It's very hilly, it's very rocky, the weather is very seasonal, so you have great dry periods followed by torrential winter storms. And all the fresh water has got to come from springs on the opposite side of the valley. Once it's in the city, the real challenge is moving it around to where it's needed. Sometimes the water's going downhill, but sometimes you've got to pull it up.
The Minoans thrived here because they understood a basic principle of water. It always finds its own level. So by using a stream on the nearby hill, they were able to direct the water down and up again across the city. With water reaching wherever it was needed, the Minoans could build networks not just for water, but also for drainage and sewage. And these networks were built to last.
So we're really lucky to be allowed here because at the bottom of this hole are in situ terracotta pipes. Now the pipes were designed to bring the fresh water in for drinking. They're a very special shape, sort of like a very long, thin cone. So the entrance at one end is slightly wider than the exit at the other. This allows them to fit together really snugly, excluding air and making sure that water pressure is maintained within the system. Terracotta is a fabulous material because it doesn't matter what you're putting through it, whether it's acid or alkali, it will remain unchanged for thousands of years. The pipes laid down here are as good today as they were when they were first laid.
Such attention to detail extended to their sewage network.
I'm standing on the oldest road in Europe. 4,000 years ago, when engineers constructed this, they put in a huge central drain to take all the water from the palaces and the courts above it. The most amazing thing is, it all still works.
Their longevity is thanks to meticulous engineering.
We've got this lovely sinuous line as the drain snakes around the hill, and that's for a very specific reason. It's all about controlling the flow of the water. While you want it free flowing so you can avoid blockages, you don't want it just shooting off down the hill too fast because that would erode the bottom of your drains and cause it to collapse. What we have here is very careful management of that flow rate. I mean, this is really very clever. It's built to last.
Defying the ravages of time, the system is still draining rainwater from the city.
This city-wide network is remarkable. Hydraulic engineering began here, and it's the basis of everything we do today.
At the super sewer, engineers must ensure the buried network will remain as maintenance-free as Knossos. The sheer capacity of the shafts will help control any surges. But the bigger problem is waterproofing. Existing methods can be challenging for such giant and complex structures.
To apply a sheet membrane waterproofing system is quite labour intensive. It requires access at a later stage along all sides of the shaft and at height, so it becomes a safety risk. So if you can reduce the number of processes required to complete the structural lining, including the waterproofing, then of course you're reducing the number of man-hours on the project and you're hopefully improving safety and reducing risk to the workforce.
At the shaft, there's a revolutionary solution. A chemical treatment is added directly to the concrete mix. Reacting to the water and cement in the mix, the chemicals grow into crystals, filling the capillaries. As the crystals duplicate, they create a network that stops water passing through. The impermeable barrier will hopefully be as effective as the terracotta used by the Minoans.
All right, guys, are we setting up to any batching now? Yeah, we're getting ready now, yeah.
Perfect for simultaneously strengthening and waterproofing, this innovative treatment will protect the site long into the future.
Okay, so we're now batching the concrete mixture. So just behind me you can see two silos that are both batching at the same time into one pump. The material goes into the hopper behind me and the pump then pumps the concrete mixture in this line all the way to the drop shaft for use in the spray concrete lining construction.
The exposed ground in the shaft is unstable, so the mix is designed to set quickly. With excavation temporarily halted and emergency breathing apparatus at the ready, it's safe to enter.
Right.
Each 1.2-metre vertical lining requires 130 tonnes of the mix.
Around here. Cap is a bit slippery.
But there's a risk the mixture will set before the work is completed.
Okay.
The solution is an ultra-high pressure pneumatic hose.
Don't cross the red and white line, basically. Simple as that.
The mixture is propelled at 4,000 psi, enough pressure to cause serious harm.
So here we are at the bottom of the drop shaft. We've tested the mixture at the surface, and now the concrete mixture is being applied as a spray concrete lining, incorporating the crystallizing agent as a waterproofing measure.
With the pump working at full power, it takes just minutes to protect the section.
It's great to see the spray concrete lining application in person. It's really quite a challenge that has been overcome here.
With its longevity assured, the super sewer network can start to grow. The super sewer will future-proof the existing network. 36 of the most polluting CSOs will connect to deep shafts. And the shafts will be linked by 32 kilometres of tunnels that run under London.
Tunnelling below one of the biggest, busiest and oldest cities in the world presents a lot of challenges. Just finding space for a start. Here we're surrounded by listed buildings, architectural gems and historic monuments. And that's just above the surface. When you get below ground, it's even more complicated. You've got all your existing infrastructure, so that's the Victorian sewage system. It's your water main, your gas main. It's your electric cables and your telecoms cables. It's the tube and all the pedestrian walkways that go with that. And that horrible tangled network is set inside 2,000 years worth of archaeology. London is just built on more London. You can't put a spade in the ground around here without finding something interesting. And then there's the river, without which none of this will be here, but which makes the whole of the subsoil completely waterlogged and difficult to dig through. And they're not just digging any old tunnels. These tunnels are big enough to drive a double-decker bus through.
Engineers need a machine that can work under the most difficult circumstances. But strewn with obstacles and with the weight of London above them, the team face a seemingly impossible challenge. The solution is found in the battlefields of the past. In the dense scrubland of England's south coast, engineer Katie Toms is searching for a location that's been all but forgotten.
I'm really excited. This place is normally closed to the public, but I've got special permission to have a look inside, so can't wait to see what's in there.
Extending over 180 metres into the chalky earth. This is the Winchelsea Tunnel.
Lots of graffiti on the walls down here, lots of initials, which is quite nice to see the history of it, really.
The tunnel's origins stretch back to World War I. In the trenches of Flanders, Allied forces devised a plan to dig tunnels under enemy lines. Once dug, huge caches of explosives could be detonated inside them. The Winchelsea Tunnel was the secret test site for this plan and was dug by an extraordinary new machine.
So you can look at the shape of the tunnel and the length of it. It's almost a perfect circle. I could track the movement of what the machine would have been doing all the way around to here to take out the material. It must have been a big beast of a kit for its time, really quite sophisticated, so it's really exciting to learn about it.
The mysterious machine used here could hold the key for London's super sewer. And Katie has managed to track down the only example left in existence.
I have exclusive access to the Science Museum group collection. No one is allowed back here, but I've been told there's a really exciting piece of important engineering history somewhere in this building, and I can't wait to find it. It's like an Aladdin's cave. And here it is.
The Whittaker tunnel boring machine was the brainchild of English engineer Douglas Whittaker.
So this is the cutting face, you can see here. It's got the buckets on the outside. There's the cutters here, which would have excavated the material. The buckets, as it moved, would have collected it.
But Whittaker's amazing machine didn't have the best of starts. The ambitious plan in the World War I trenches failed, and his machine was left buried under the battlefield in France. And this example was part of a cancelled attempt to dig a channel tunnel between England and France in 1921.
This one is a little bit larger than the one that would have cut the Winchelsea tunnel, but the size of the buckets is similar, and that would have given the uniformity of the markings that we saw in the chalk, caused by the large rotary movement that would have helped the machine advance down the tunnel.
But despite its failings, Whittaker's extraordinary tunnelling beast contained a vital innovation. Rock contains cracks, faults and folds. When tunnelling underground, it's vital to keep the pressure balanced. If the excavated material or spoil is removed too quickly, the sudden change of pressure can cause a collapse. Whittaker had the solution.
What Whittaker came up with was this corkscrew conveyor, which takes the material collected from the buckets all the way down the length of the machine. This is a very simple mechanism, really. The material goes in as it's being excavated, and then as it moves around, the material is taken along the whole length of the machine and then is collected right at the end. It's simple.
Whittaker's corkscrew technique meant he could remove just the right amount of spoil at any one time.
The corkscrew and the cutting mechanism were calibrated to the same rate to make sure that that was balanced correctly to stop the tunnel from caving in.
Whittaker's tunnel boring machine, or TBM, was the forerunner of a technique now used all over the world.
Whittaker's combination of the rotating cutting face and the screw conveyor really have become the blueprint of all future TBMs. This is such an amazing piece of engineering.
In London, using principles engineered by Whittaker, 7 giant TBMs will dig the 32-kilometre tunnel network. Some of these machines have a diameter the length of a London bus and weigh as much as 1,300 tonnes.
And here she is.
Each has been specially engineered for the job.
This is Rachel, our tunnel boring machine, 8.1 metres in diameter. With all the backup gantries, it's going to be 147 metres long when complete.
Engineer Mark Shepherd is doing a final inspection of this machine's cutting face before it's deployed under London.
So this is the cutting wheel of the machine. It's around 100 tonnes on its own. This will do all the cutting, so we're mining through mostly London clay in this section of the tideway. This is an earth pressure balance machine, so this cutter head will be full of mined clay at pressure. The red screw at the bottom there will rotate and that will take the muck out.
Like the Whittaker machine, the screw helps maintain pressure at the tunnel face.
It's about 20 metres long in total. It runs right through the heart of the machine. And because it's so long, that can keep a plug of of material as we're excavating and hold the pressure in the face. So that's rotating, full of material, and we can control the speed of that. We have a guillotine door as well on the end, so we know exactly how much muck is coming out, so we're not taking too much out.
Because the city is strewn with underground obstacles, the TBMs will excavate deeper than all existing infrastructure, directly under the river. Lowering them down the drop shafts is a precision operation. But once in position, they'll advance 8 meters per day to connect all the shafts together.
The project is just enormous.
Site manager Paul Hallows is venturing down to one of the biggest tunnels on the project. Having already excavated 300 meters, he's inspecting one of the mega machines in action.
It's absolutely enormous. We still get the buzz every day from coming here. So, we're at the front of the TBM now. Just beyond me, you can see, that's the bulkhead. Just beyond the furthest away part, you can see the TBM. That's where the cutting disc is, which is turning about 2 RPM. Beyond that is the earth. Above us is the river. We're at the business end. All the spoil in front of the TBM, that's being cut away. It's then dropping down into the invert in the front of the machine there. Coming up this screw conveyor here, dropping down into the conveyor, then it's away, all the way down the tunnel on conveyor belts, up to the surface, and gone from sight. This is a huge undertaking in the centre of London. Cheers.
As the cutter moves forward, Paul and the team build giant concrete rings to support the new tunnel. The further the TBMs travel, the more segments are needed. Up at the surface, a seemingly endless supply keeps the TBMs fed. With access through London's streets so difficult, the segments are transported by barge along the Thames. Safely on site, they're craned down the shaft to join the TBM's automated production line.
Each tunnel ring gets brought into the tunnel by the loco, it's put on the storage cassettes. From the storage cassettes, it's picked up, carried up to the front. You know, this is one of the last segments of the next ring. This weighs in excess of 5 tons, something like that, depending on which plate it is.
At the front of the machine, the huge segments are picked up by suction, rotated to where they need to be, and fixed in place.
We excavate in 1.8 metre increments. So every time we advance 1.8 metres, we retract the rams, we build one of these concrete rings. These concrete rings, 1.8 metres wide. There's 8 of these sections make a complete ring. There's over 40 tonnes per ring. Once a complete ring is then built, then we can excavate, start again, start another 1.8 metres. This is what we're going to be doing for the next 4,500 metres.
The giant tunnel boring machines are the solution to the London super sewer's seemingly impossible engineering challenge. They can quickly and accurately thread their way through London's tangle of underground obstacles. And it's all thanks to tunnelling pioneers like Douglas Whitaker.
The engineers of the past, you can only be impressed by them. Everything we're doing now is as mechanised as possible. Now we're just concrete lined, rapid progress, much better environment to work in, but hats off to them. I wouldn't have liked to have been around then.
The shaft is so deep, it could swallow Big Ben here. And there's a really good reason for that. It's about creating the perfect self-cleaning velocity. And you do that by controlling gradient. Too shallow, nothing goes anywhere. Too steep, and the liquids separate out from the solids, leaving them behind to accumulate and form blockages. Over the 30 kilometres of this tunnel, the perfect gradient dictates that you have to end up 88 metres below ground.
So we're now on the west side of the pumping station.
At the pumping station, engineer Jad Boudia is venturing all the way down to the bottom.
So this is the lowest point in London. that you can physically and safely get to.
From here, accumulated sewage must now be pumped to the treatment works for processing. But pumping tons of semi-solid material 88 meters vertically upwards is a huge challenge.
I don't think there are any pumps available in the world which actually pump the 88 meters, so this project is unique in terms of the depth.
To find a solution, engineers looked to the groundbreaking innovators of the past. A third of Holland lies below sea level, at the mercy of the water. To keep their land safe, the resourceful Dutch people had to keep one step ahead. First, they built hills to keep dry. Then they built dikes to hold the water back. Then they built windmills to drain the land. But there was one area where none of these were enough. The Friesland region is a 5,500 square kilometre area of flat land bordering the North Sea. Its history is punctuated with fierce storms and devastating floods. Marine engineer Kees Storm has seen the damaging effects on the land.
Friesland is one of the wettest areas, and that's because north, west and south we are surrounded by water. So that was always our biggest problem. Well, with a couple of days of storm, the enormous amounts of water inland, which could be millions and millions of cubic meters, would take months to get rid of. So you really need a significant engineering solution to do that.
Saving this land seemed an impossible challenge, but one Dutch engineer thought he had the answer. In the early 20th century, Dirk Frederik Woeder perfected the pump system. And in 1920, he built this. The Woeder pumping station. At the time, the largest and most technologically advanced steam pumping station in the world. And it could hold the key to the super sewers problem.
I love coming in here, and it's a beautiful sight to see the machine running smoothly and steadily.
The heart of the station was the centrifugal pump. Inside a centrifugal pump, a shaft-driven blade called an impeller rotates. As the impeller accelerates, fluid is sucked through the inlet port at the center. The velocity propels the fluid to the edges and out through the discharge port at the top.
Well, as a marine engineer, on board of ships we used also centrifugal pumps. But I've never seen a size like this, with a man's height and even higher.
The giant pumps are driven by enormous steam engines. And these steam engines were originally fed by 8 large boilers. Similar to those used on the recently built Titanic, there was more than enough power on tap.
So these massive pumps require a lot of horsepower, and that's why we require each engine to have 500 horsepower, which is equivalent to a beautiful sports car. Just to give you an idea of the capacity of all the 8 pumps, if you fill up this whole building up to the rooftop with water, and all the pumps are running like now on a steady speed, the whole building is empty in 2 minutes only.
The ability to shift such volumes so quickly is thanks to the gravity-defying engineering inside the pumps.
To show you what is working inside the pump, I will do a demo. And the first thing we will do is build the impeller. And we do it very simply by attaching the tube onto the pencil, like this, cutting the ends off, and then attach the impeller into the drill. So now my impeller is ready. Now we are going to prime the pump as we do in the main unit.
To prime the pump, water is sucked into the tube.
The pump is now primed, And if we start rotating, oh, there he goes. The centrifugal forces overcome the gravity and the pump starts pumping and getting me very wet.
The brilliant simplicity of this ingenious system allows Wuda to continue pumping vast amounts of water even today.
Now, even 100 years old, these pumps are still doing their job and are very important to keep the country dry.
"88 meters below the ground in London, engineers have installed the solution to their pump problem. Dwarfing even those at Wuda, the centrifugal pumps here are so large and so powerful, they must be encased within concrete 4 meters thick.
The technology of centrifugal pumps has been around for a long time. The only difference with the Lee Tunnel project is that the size of them are unique in the sense that they've never been made to this size. The pumps are really big here, they're effectively 2 stories high.
Weighing over 50 tons, with a 2.2 meter diameter impeller, the pump can move the equivalent of 3,000 liters per second. And there are 6 pumps.
The centrifugal pumps can actually cope with a lot of solid material, and it would be very difficult to actually take this up to ground level without pumping and using the pumps that we have. No other pumps would have the capacity or the duty to pump out the Lee Tunnel.
Like Wuda in Holland, the pumps need a lot of energy to drive them. On the next floor are 6 motors, weighing 30 tons each.
Each motor is approximately 3 meters by 4 meters square. These motors generate 3.5 megawatts, so very large power usage for the motors to drive the pumps. These motors have a central shaft, which then is connected to the impeller itself.
Such vast motors are power hungry, and part of the solution to this problem is above ground. This is Beckton's sewage treatment works, the largest plant in Europe.
We're standing on the flow collection chamber where the 6 pumps pump up to this level. They then transfer the flows through steel pipes up to the inlet works for distribution into the sewage treatment works.
At the sewage works, the wastewater settles in giant sedimentation tanks before bacteria breaks down and removes impurities, including ammonia. The process releases natural gas, and some of this can be recycled for energy production across the site. With the pumps running at full capacity, Beckton processes 2.3 billion litres of wastewater each day. Enough to fill Wembley Stadium. Twice. And all this cleaned wastewater is returned safely to the Thames.
It was a brilliant experience to see the pumps operating for the first time 3 years ago. So it's a great feeling working to clean up the River Thames, and I feel proud.
Since its inception in 2010, the super sewer has grown 30 kilometres from west to east London. This mega project is one of the biggest infrastructure works in Europe, including 6 of the biggest wastewater pumps ever used in Britain and the biggest and deepest shaft ever sunk in London. It has a storage capacity of 600 Olympic swimming pools worth of sewage. By the time it's completed in 2024 and the 34 worst polluting overflows are connected, pollution in the Thames should be reduced by up to 97%.
By connecting the most polluting CSOs to 24 new shafts, the super sewer will revolutionise the existing Victorian network. Millions of tonnes of sewage will be carried along 32 kilometres of tunnels, ending at London's deepest shaft 88 meters below ground. After being pumped up to the largest treatment works in Europe, billions of litres of safe wastewater can be returned to the Thames. The new super sewer has pushed the boundaries of construction.
The feeling now when we come into the tunnel, both myself and all our team, immensely proud of where we've got to. It's a very empowering position to be in.
By drawing on the innovators of the past and conquering the many challenges, the project will improve the lives of 9 million Londoners.
I want to have an impact on the London area, the local residents, and being a Londoner myself, I have a clear passion for making sure this project is a successful one.
And its success will be far-reaching.
The new super sewer will serve this city for the next century and beyond. It will reconnect the people of London with their river. The success of the project will stand as testimony to the ingenuity of today's engineers.
The super sewer team have succeeded in making the impossible possible. Dubai, in the United Arab Emirates, home to some of the most innovative engineering on the planet, where each new build must push the boundaries of what's possible if it's to stand out from the crowd. One man who knows what it takes to make your mark on this ever-evolving city is Mohammed Al-Mula.
Dubai has been able to prove that there is no limit to your freedom of thinking. It's important that we keep pushing the boundaries of engineering across every project we do. Dubai known to be bringing the best in class in various aspects, from the tallest towers to the biggest airport. I'm sure Dubai in the next few months will be another mega project that will be announced. Once you have a dream, people will get together and just help you to achieve that dream.
This desert city must continue to create the spectacular simply to survive. But Dubai's prized waterfront locations are rapidly running out, meaning engineers must think radically.
The coastline in Dubai has a limited stretch. You have certain type of tourists who look for beach, so we must make sure we have enough beaches. We must extend the coastline. It's very important for our survival to move forward in a very competitive landscape.
But creating land where there once was none presents a monumental challenge. For centuries, man has been trying to make the most of the coast. In the early 1800s, the new craze for seaside holidays saw the British extend their seafront with the first pleasure piers.
Phew!
And in 1905, Abbot Kinney carved extra waterfront living by cutting canals inland, creating Venice, California. But engineers in Dubai are characteristically thinking much, much bigger. They're creating a whole new island. This is Bluewaters. Where once there was nothing but water, now stands an entirely new city district. And not only that, a world-beating megastructure is also set to take residence. The Ain Dubai, the planet's largest ever observation wheel.
This is the most challenging engineering project happening in the world at the moment.
When you arrive, you'll see the wheel. It will be a moment, a wow moment. I'm sure everybody's jaw will literally drop and they'll just stand there in awe.
constructed from 800,000 cubic meters of rock and 4 million cubic meters of sand. Bluewaters Island covers an area larger than 12 New York City blocks and will be populated by a combination of residential towers, shops, and 5-star hotels. Its crowning glory is an observation wheel on an unprecedented scale. Standing more than 250 meters tall, this giant of engineering tops out at almost twice the height of Britain's iconic London Eye. But this multi-million-dollar project poses huge engineering challenges. How to create land where there is nothing but sea?
Bluewaters Island is a very challenging project for us because desert sand is not suitable for island construction.
How do you make it strong enough to support tower blocks and a megastructure?
Loose sand, it's very limited in the load that it can support. Typically maybe 10 to 20% of what you would expect on traditionally formed ground.
And how do you build a wheel that dwarfs every other wheel ever constructed?
These cables have to be very strong, but if we put all the tension in the bottom, we would just buckle the rim.
Bluewater Island, we keep on pushing our boundaries.
280,000 square meters of reclaimed land containing an entire city district, where once there was nothing but sea. It's topped by the biggest observation wheel ever built, standing 85 stories high. But in order to achieve this world-beating feat of engineering, the team behind it must overcome major challenges.
Okay, let's go.
Civil engineer Koen Sweers heads up island construction.
It's a good day for surveying today, I think.
Perfect day.
Building begins by uncovering what lies beneath.
We start the island with what we call an in-survey, where we map the seafloor, where the future island will be, and that's basically our starting point.
Sonar and GPS allow Koen and the team to precisely map the sea bottom.
Oh yeah, you see it there popping up on the screen. Yeah, perfect. So here now it is 7 meters, eh?
Yeah, exactly. It's between 7 to 9.
Yeah. Based on that, we can calculate up till the design level of the island.
Building Bluewaters will require a staggering 4 million cubic meters of sand. But despite being located in the world's 5th largest desert, finding the right sand is far from easy.
Desert sand is not suitable for building an island. The sand particles of desert sand are very round, and this is not good for the interlocking between the individual grains. It's like you have a jar with all of the same marbles.
So, engineers must use sand from below the sea.
We use marine sand. Marine sand is very suitable for construction works because it is much more angular. And marine sand has a lot of particles of different gradings. And it is coarser, so it settles much more easier.
With marine sand sites 30 nautical miles away, engineers are facing a giant challenge.
Instead of bringing sand by road transport to the location, we have to find other means to bring the material from sea to the location of the island.
It's a mission that would be impossible without the great engineering pioneers of the past. Miami Beach in Florida. Today, it's one of the most glamorous and prestigious coastal resorts on the planet. But little more than 100 years ago, it was a desolate, swampy wilderness. Its success is down to the vision of one man, Carl Fisher. He planned to convert this quagmire into what he called the prettiest little city in the world. Mechanical engineer Dan Dickrell is on a mission to find out just how he did it.
Oh man, this is amazing! What a unique experience driving an airboat in the Everglades. Yeah, this is the natural Florida.
In the early 20th century, Miami's coast was a very different place.
Oh yeah, I'm gonna go a little bit more up ahead. There's a good spot right up there. Perfect, perfect, perfect. Okay, so this is what Florida used to look like. The land that Fisher bought would have been very, very close to this. Oh, it's super soft. There's mud and silt in there. From an engineering perspective, there's nothing that you can build a solid foundation upon.
Yet despite the makeup of the South Florida swamps, Fisher was undeterred, believing engineering had the answer.
So this vessel is a hydraulically powered cutter suction dredger. It is the same type of thing that Fisher believed he could use to realize his vision. Now I'm going to give these controls a go and see how it functions. On the end of this large boom, we can see gnarly looking cutter wheel. I can move it up and down. I can move it left, and I can move it right, all right? If I turn this knob here, we transmit power to the cutter head. So now this cutter head's gonna rotate. As I drop it down, I'm gonna engage the bottom. Now what's gonna end up happening is I'm gonna start removing material. And as that material is removed, it's being transported through that orange hose. That's a discharge hose. That discharge hose is connected to a hydraulic pump, which sucks the water and solid material through and transports it a long distance away to trucks or back on shore.
For Fisher, cutter suction dredging offered the perfect solution. The mangroves could be cut away and the dredged materials used to create an island, just like engineers in Dubai want to do. Between 1914 and 1928, Fisher's dream began to take shape, much to the amazement of those that had doubted if his plans were even possible.
And this is the end result of Fisher's ambition, Miami Beach. So standing here looking out from an engineer's perspective, it's an outrageous idea to imagine Fisher took a swampy wasteland and turned it into one of the premier beaches of the world. Talk about making the impossible possible.
Back in Dubai, engineers are pushing Fisher's idea even further, reclaiming vast amounts of sand from the depths of the Arabian Gulf.
For Bluewater Island, we need 4 million cubic meters of sand. You can compare that to 2,000 truckloads of sand each day, 7 days a week, for 5 to 6 months long. So we mobilize dredges from around the world.
To achieve this Herculean feat, the team begin by using a supersized version of the vessels used to transform the Florida swamps.
We used cutter suction dredges. These dredges, the harder material that we encountered. Then we used trailing suction hopper dredges. Basically, it is a vessel with a big vacuum cleaner on the side. They suck up a mixture of sand and water from the sea bottom.
Gathering the sand is one thing, but engineers now face another problem. Once the shape of the island has been outlined, using rock and protective textiles, how do you deposit such enormous volumes of sand?
In the first phase of building an island, when there's still sufficient water depth, Then we discharge the material by opening the bottom doors of the vessels.
But as the island grows, engineers must turn to other ways of depositing the sand.
One is what we call rainbowing. You will see a rainbow of water sands flying through the air straight to the location where you want it to be. We use that technique at Bluewaters quite a lot.
When the mighty vessel can't get close to the island, engineers have a further trick up their sleeve.
You see on the bow of the vessel this round cylinder construction. From there it will connect to a floating pipeline and then it will pump the material through the floating pipeline. We can pump, if necessary, a few kilometers away into a series of shore pipelines in the location where we want the material to be. These kind of vessels are crucial. They basically do the hard work. We come and there's nothing, and we leave and there is an island. So yeah, it's tremendous.
Where once there was nothing but ocean, Bluewaters offers developers an impressive 280,000 square meters of prime coastal real estate to build on. It's enough space to construct an entirely new district for the city. David Murray is a leading engineer involved in this seemingly impossible transformation.
We inherit a site that contains very, very loose material. It's really due to the nature of how the island has been formed. The sand is pumped and sprayed into position, so there's no real compaction process. And what this means is that the sand has got a very, very low strength. When a structure is built on top of that sand in its loose state, it's prone to substantial deformation and settlement, because as the weight of the building pushes it down, you get a lot of movement, and that can cause a lot of damage to a building and can make it unsafe. So it needs further treatment to provide extra strength and stiffness.
Might the answer to this problem lie with the innovators of the past? Man has long understood the importance of solid ground to successful construction. If your foundation isn't firm, then your structure will be unstable. And when it comes to transport, travelling over surfaces that are too soft could leave you stuck in a rut. Andrew Steele is in the British Midlands, putting his back into some good old-fashioned manual labour.
Well, that's a nice big pile of sand. Let's try flattening it out. Here goes nothing.
In the early days of road building, heavy cast-iron rollers were a typical tool for compacting foundations.
Well, this really isn't a very practical method.
Making it a slow and expensive business. As the importance of a modernised road network grew, so did the need to get it built quickly.
You can see why they wanted to try and find a more efficient, faster and cheaper way of flattening out sand than this, because this is ridiculous.
Luckily for Andrew,
now this is more like it.
In 1867, two engineers came up with a solution.
This is an absolutely incredible machine. Look at her roll.
Pioneered by Thomas Aveling and Richard Porter, the steamroller marked a watershed moment for heavy industry. And this 125-year-old example is one of the oldest surviving rollers on the planet.
This thing's just a beast. Look at the size of these cast iron wheels and the power of the steam that we're using to get this thing rumbling down the road. Oh, I wish it had power steering though.
Weighing in at an earth-shaking 10 tons, this monster machine is a powerhouse when it comes to compaction.
Right, let's see if this thing can do any better. Much more fun. What a beautiful, impressive and powerful bit of kit. Well, that is much better than my shoddy attempt. Not only did we manage to do it in a single pass and cover a lot more area than I managed manually, but if you get down close, you can see this sand is much more compact and firm than I could manage with that little manual roller. Looking at this, it's obvious why that machine was such a hit.
But there was an unintended side effect to these early steamrollers. One that could be important to the engineers of Bluewaters Island.
Because they were often driven in a very low gear with high revs, and engineers started to notice that this front roller here would be vibrating. Now, this actually has a benefit when it comes to compacting a road surface. And so I'm going to show you a little demo to try and explain why that is. So what I've got here is a plastic cup, a little bit of breakfast cereal here, and I'm just going to pour the breakfast cereal in. There we go. And now to simulate that vibration, I've just got a bit more of a modern tool, this electric drill. So if I just apply a little bit of vibration, oh wow, that worked very quickly. You can see those little grains of rice in there. They're just moving around pretty much at random. And what that means is that they're settling down to their optimal positions.
As the vibrations cause the grains of sand to jostle, they begin to slot closer together, closing up the air pockets and improving compaction.
Having noticed this, engineers building modern versions of this steamroller would actually intentionally build in that vibration to try and take advantage of this effect.
The introduction of the steamroller went on to revolutionise road building in Britain and beyond.
This beautiful machine was fundamental to the past and still continues to shape our future.
Engineers in Dubai use an arsenal of heavyweight machinery to shore up their new island. Among them is a descendant of Aveling and Porter's traditional steamroller.
So this is a 27-ton vibrating roller. Now you can feel actually the effect on the ground. It's shaking beneath our feet quite dramatically. As it rolls, it also vibrates. So it has a very good compacting effect. You can really feel it now, so it gives you an idea of how much shaking and vibration of the ground is happening. This machine is rolled over the surface of the sand, and what it does is it densifies the sand to give a very, very strong capping layer.
Vibrating rollers can compress the top 2 meters, but the challenge here goes much deeper. To fully compact the millions of cubic meters of the island's sand, engineers need an extra tactic.
In order to overcome the various risks associated with loose soils, we undertake a ground improvement process, which in this part of the world has become very successful, and it's a process called vibrocompaction. Okay, take it up.
It's a technique made possible thanks to yet more supersized machinery.
So we're now looking at a typical poker assembly. The majority of this will be underground during the compaction process. You can just get a sense of the scale of this when you look up. This is 25 meters long. We're talking about 4 or 5 story building in terms of the depth of improvement that goes below the ground.
Vibrocompaction begins with the poker penetrating the ground to the required depth. As the poker vibrates, it's raised up in stages, causing the sand to compact around it. The crater that develops on the surface is backfilled, then re-levelled and finished using the vibrating roller.
The great thing about this is it's a very quick way of compacting the ground, what we call an accelerated compaction. We don't wait for hundreds of thousands of years, we do it instantly.
But with plans for multiple towers and a massive megastructure, engineers will need to further bolster Bluewaters Island.
If you're building a very lightweight building, 2 to 3 stories, in general, yes, you can build off ground like this. But when we're talking about taller structures and megastructures, this material on its own won't have sufficient capacity to support the ground. It does give a contribution, but not the entire support to the structure.
Huge concrete piles help to underpin the biggest builds.
Those piles have to be anchored deep down into the rock. They don't just sit on the surface of the rock, they actually extend 10, 15, 20 meters down into the rock. And there's a friction between the pile and the rock which stops it from pulling out.
With the ground compacted and foundations deployed, engineers can finally begin to build. Residential towers, luxury hotels, and retail parks all rise up to take their place in the city's crowded skyline. But the biggest challenge of all still remains: how to construct the planet's largest observation wheel.
It's like Piccadilly Circus round here. Can I go around here, guys?
Project manager Piers Sidey is the man overseeing this record-breaking build.
There are obviously other observation wheels around the world, but we're about 50% bigger than the current biggest.
Once complete, the Ain Dubai is set to rise over 250 meters above the Arabian coast. It will be almost double the size of the giant London Eye, making it comfortably the largest wheel on the planet, and will set a world record that some believe will never be broken. 48 specially designed pods made from aviation-grade glass will carry 1,900 passengers. But supporting this massive structure requires a framework on an equally epic scale.
So the main components of the structure, we have 4 legs, 900 tons each, 125 meters long.
And with the streets of Dubai packed with traffic, road transport of this giant component would be impossible.
Really, transportation was only going to ever be by water, so because we're on an island, we bring them in by barge.
Each giant leg weighs more than 5 747 jumbo jets. But on a build of this size, the problems just keep getting bigger.
The heaviest part is the hub and spindle, which connects all the legs together and carries the 6,500 ton weight of the wheel.
However, to raise this near 2,000 ton component to the required 126 meter height meant more problem solving.
So we can put a block on that top platform, pick it up and lower it off. So otherwise we can't get a crane to it.
Yeah.
Is there anybody working on this side as well?
The only way to conquer this supersized challenge is to use supersized technology.
We lift them off with 2 of the largest cranes in the world. $3,000 ton capacity units.
Bump the touch to the right.
Working at about 98% of their safe working capacity.
Stick boom down, 20 centimeters or so. You gotta go like a hair to the left.
The biggest tandem lift, and certainly the highest tandem lift that's been done before.
Keep coming down, looks good. Okay, stop.
Hi, how's it going? Good. Gonna go up to the top of the spindle.
Engineer Darren Brooke has special clearance to climb through one of the mighty legs to the spindle itself.
This is completely restricted, so no public access. We've just entered leg 1. The legs are inclined at about 16 degrees, so this lift also then travels up the profile of the leg. It had to be specially designed to meet that angle. Here we are at the top. Well, almost the top. We've got a 9-metre climb now to go. So where we are now is in the middle of the spindle. The spindle is approximately 135 metres in the air. As you can see, it's a vast space, 6 metres in diameter. It connects the 4 legs. This space is big enough to fit 2 buses in. Running round the outside of that, and we can just sort of see through these hatches here, is the hub.
The gigantic rotating wheel will eventually be attached to this unit.
The hub is actually the moving part and actually contains all of the bearings that then run over the spindle. The hub itself, that's really transferring all of that load into the spindle and then to the legs and then back down to the ground and the foundations.
It's an impressive achievement. But on a project of this size, there's always another challenge that lies ahead for engineers.
With a wheel of this scale, I think the biggest challenge is trying to foresee the unexpected before it happens. The rim is built in 8 sections, lifted off the barge, welded together, launched with a special push-pull system.
Supported by massive steel wagon wheel-like spokes spanning the radius, engineers weld one section of rim to another, push and pull it around, then weld on the next section until the circumference is complete, revealing the wheel assembled for the very first time.
I think it is a particularly beautiful wheel. We've had lots of things for the designers and the erectors to overcome, and we've managed it.
But in order to complete this world-class wheel, one final impossible challenge stands in the engineer's way. The wheel must support itself without the aid of the 8 large steel-framed spokes.
It was part of the brief that this had to be aesthetically beautiful, had to take it the next step beyond some of the other wheels to create a very light-looking structure. So we need to keep the weight down, but keep the strength.
To keep the wheel strong, stable, and yet still lightweight, engineers will need to draw on an innovation from the past.
This is pretty cool to be here and just can't wait to get up.
Mechanical engineer Melanie Todd is in Vienna to take a unique look at an epic engineering feat.
Let's go.
The Wiener Riesenrad, the oldest Ferris wheel on Earth.
This is so amazing to see the whole structure so close, and we can even see the wheel moving.
At almost 65 meters, it was once the largest.
I'm touching one piece of history here. This wheel was actually built 120 years ago. This is really amazing.
But it wasn't the first. In 1893, American engineer George Washington Gale Ferris Jr. designed the first ever fully circular, large-scale observation wheel. The Wiener Riesenrad was built on similar principles to Ferris's revolutionary wheel.
When George Ferris came up with this idea, people thought he's crazy because no one could believe that something that thin, that slender, could carry its own weight. They did not even think that such a wheel can be built.
Ferris was determined to prove them wrong. But just like the engineers in Dubai, he faced a huge problem.
Ferris needed to find a lightweight design that can carry its own weight. To realize this construction, George Ferris used a principle that is called pretensioning, and this is a principle that allows such thin constructions to carry much more load than without the pretensioning. It's the same principle as the wheel of a bike.
Old small fairground wheels used large heavy beams to support their outer rim, like a wagon wheel. But Ferris realized that like the spokes on a modern bicycle, he could use relatively thin wire or cable to make his wheels strong. These cables would have virtually no strength in compression, but as long as they were tightly and evenly tensioned, they would be more than up to the job.
It's fascinating to see actually how the cables are mounted to the spindle.
To truly experience Ferris's innovation for herself, Melanie is going to take it for a spin.
Danke. It's so smooth. George Ferris actually reinvented the wheel. He brought lightweight design to new limits. Due to his achievements, it's now possible that we have this kind of huge observation wheels.
More than a century on, engineers in Dubai are taking Ferris's idea to even greater heights.
The concept was to create something that was amazing and just awe-inspiring. To create a structure that did look lightweight, but keep the strength.
By using pre-tensioning, the wheel's temporary rim supports can be removed, leaving only the slender cables to carry the load.
And to do that, we've used some very high-strength steel. These cables can take over 300 tons of load.
Despite using super-strength cables, engineers still rely on basic principles.
You can actually liken this wheel to a bike wheel. You can't actually tension all of them at once at one area because it will just buckle the rim. And it's exactly the same challenge we face here on a wheel of this diameter.
Huge hydraulic jacks tension 24 cables at a time. The wheel is then turned and the process continued until all 192 cables are tightened. At 100% tension, each cable can hold 300 tons, the equivalent of 50 African elephants. It's another example of the innovative solutions that make up this groundbreaking wheel. A structure so massive that it dwarfs the competition.
So we're 135 meters in the air. We're looking out over a beautiful Dubai landscape. We get a fantastic view from up here. If we were at the London Eye, we would now be at the very top. However, in Dubai, we're only at the centre. We're not just making the largest wheel, we're going up by orders of magnitude in terms of the largest wheel. It's a phenomenal project, it's a phenomenal undertaking.
For the team behind this audacious build, the scale of the achievement is undeniable.
We've been breaking the engineering mould all the way through this project. We're pushing the boundaries on so many levels.
As a structural engineer, you're constantly challenged. Things that 10 or 20 years ago people would have felt is just not possible. It is possible now.
It's the world's largest observation wheel, And to do that, we've had to employ a great team of people using some of the largest equipment in the world to actually build it.
I think when we see the first passengers take their rides on the wheel, it'll be a huge sense of relief and satisfaction and pride to have been part of this great team.
The magnificent island that has risen from the ocean floor. The city district that stands where once there was only water. And the megastructure that crowns it all, towering hundreds of meters above the coastline. All stand as testament to the groundbreaking work engineers have done. It's a feat that all involved are rightly proud of.
In my opinion, this is the most challenging engineering project happening in the world at the moment. And personally, I've been very proud to be involved since the beginning.
By learning from the great pioneers of the past, adapting, upscaling, and overcoming huge challenges.
It always pushes me to the boundaries. And the nice thing about it is that you have created something that will be there for the next 50 or 100 years. And that's something that gives incredible satisfaction.
Engineers have continued to push the boundaries. In a city where the sky truly is the limit, they've succeeded in making the impossible possible.
We went with the assumptions to break every norm, every parameters, till we prove it doesn't work. And guess what? Working with the best in the world, we've been able to again put another mega project up and running, and we are proud of that achievement, another achievement for Dubai.
The Coast Mountain Range of British Columbia. 1,000 miles of vast chasms, towering walls, and ice-crowned peaks. Wendy Robinson lives and works in this extreme environment.
It's an incredible place to be. I myself am definitely a mountain enthusiast, so I love this location, whether it's winter or summer. Especially on a day like today, right? It's gorgeous bluebird, you've got the clouds rolling in and out. It's probably the best place on earth. But we're on the coastal range, so we do have constantly changing conditions. Extreme winds, extreme weather, you do get a lot of snowfall. Right now, I think we're sitting at about 9 meters of snow fall this year, with more to come. And so snow is definitely a factor.
It's an environment that humans have been trying to conquer since the beginning of time. Man has often happily lived side by side with snow. But when you add mountains to the situation, survival becomes a lot more difficult. Getting from A to B is a nightmare. There are hazards everywhere. And even if you manage to build a home there, keeping it is far from straightforward. But there's one place where engineers are taking on all these challenges on an unprecedented scale. This is Whistler, British Columbia's most famous mountain.
This pretty much scores at the top of the list for challenging sites.
It's not just the snow, it's any time that you're working at the top of a mountain. You have to deal with wind, rain, lightning. We can get hail. It makes it very difficult to build in this environment.
Whistler has among the highest snow loads in the country. It takes a certain type of engineering and construction method to build in a town like this.
Conquering Whistler requires impossible engineering. Mega muscle in the air and pure power on the ground. Engineering that goes with a bang and technology that defies nature.
So Whistler Blackcomb, we're always trying to stay as innovative and ahead of the curve with what we do. This is by far the most extreme project I've ever worked on.
Whistler is the biggest and busiest ski area in North America. It has a record-breaking cable car with an unsupported span stretching a staggering 4.4 kilometers. And the highest altitude suspension bridge in North America.
We're at the peak of Whistler Mountain, 2,200 meters at the very top, so the top of the Whistler Peak Express Chair and above everything. It definitely takes a lot to build in an environment like this with the conditions that we deal with, but when it comes down to it, this is probably one of the best places on Earth.
When you're fighting nature on this scale, ordinary engineering just isn't enough.
Pretty remote and hardly accessible, so how would you get a land crane up there? You'd have to build a road.
You guys all set for me down there?
Me and my crew are just on our way, and we'll be about 10 minutes or so.
Yeah, you bet. We'll wait for you.
Copy that. Thanks, Ken.
Jeff Van Driel is one of British Columbia's avalanche technicians.
So we're driving on Highway 99 here. This section is known locally as the Duffy Lake Road. I think a lot of people think of snow as being this soft, fluffy material, but avalanches have a significant amount of power and enough to destroy vehicles, to destroy trees, destroy buildings. They are a force of nature to be reckoned with, for sure.
Avalanches have ripped through this landscape since time began, wreaking havoc and taking lives. Stopping them is impossible.
We are not going to be able to stop the avalanches. They are going to run one way or another. The worst case scenario would be that uncontrolled avalanches would hit the highway. Our job is to maintain the safety of the road and keep it open.
To help Jeff and his colleagues take control of one of nature's wildest and most destructive phenomena, they'll have to draw inspiration from the early pioneering mountain engineers. Mechanical engineer Dan Dickrell is in Flagstaff, Arizona, exploring a solution that came out of left field.
Are you ready? All right, here we go. That was a little high. So the game of baseball is a pretty old game, and the game itself is unchanged since the late 1890s, basically. What's interesting is the technology that surrounds baseball has evolved, though. So what we're doing right now is having a bit of batting practice. As the afternoon wears on, the accuracy of my pitches slowly deteriorates, but we use technology to enhance this practicing experience and take a little load off this old arm of mine. All right, here we go. Ooh, that was a good one.
In the 1950s, baseball practice changed forever with the invention of the pneumatic pitching machine. Finally, human pitchers could take a rest.
This particular machine would be the grandchild of the original pneumatic pitching machine. I'm gonna take this baseball and I'm gonna drop it in. As I do, the compressor builds up air pressure in here. Once it hits a pressure that is sufficient to give me the exit speed that I want, all of that stored up air will be dumped into this barrel, forcing the baseball out and propelling it down towards the batters.
But one man saw the potential for this technology to be used in an altogether different way. Monty Atwater had tried various methods of setting off controlled avalanches, including artillery and dynamite blasting. But after seeing a pneumatic baseball pitching machine in action, he had a brainwave.
Oh, check this out.
This is Monty Atwater's Avalauncher, one of the last remaining examples of his literally groundbreaking idea.
If we look at it, we see this vessel here. This is where the compressed air goes. An air compressor gets hooked into this, pumping air in, pressurizing it, building up that charge.
Instead of firing baseballs, Monty's Avalauncher packs a much bigger punch.
So I've got my explosive projectile. It's got some stabilizing fins, a remote detonator, and then I would drop it in, and then we would trigger it. Projectile would shoot out. Ultimately, when it landed, it would detonate and hopefully trigger an avalanche. Now, the reason why this barrel is so long is because the longer the barrel, the higher the velocity of the projectile coming out. The higher the velocity, the further distance, the bigger the range that you'll have for this avalauncher.
This pneumatic-powered launcher was capable of firing explosive projectiles a whopping 370 meters into a mountain, starting avalanches from a safe distance.
This was a great solution to that problem of how do you trigger an avalanche without putting the people that work on the mountain in danger themselves.
All over the world, new generations of avalaunchers are used to set off controlled avalanches from a distance, and so reduce the chance of a catastrophic disaster. But high up in the mountains surrounding Whistler in British Columbia, avalanche teams need engineering on a whole new level.
Well, this is my office. It's a beautiful place to work, that's for sure.
Jeff Van Driel is in charge of a new detonation system that pioneering Monty Atwater could have only dreamed of.
What do we got for temperatures up here?
I think we're looking at -2 right now.
The consequences of an unexpected avalanche up here could be disastrous.
As we approach Blowdown Peak, path 51 here, you just see the road is just a sitting duck right underneath of it. And so our job here is to maintain an open highway by controlling the avalanches so that we can control when people are exposed to the avalanche problem.
But the 21st century solution has risen to new heights.
We're at about 2,300 meters, and what we're looking at here is the solution to our avalanche problem. Yeah, Ken, so if you want to just bring us right up to the summit there.
Front of the shack there?
Yeah, that's perfect.
Okay, perfect. Yeah, I'll plan to make an approach. I think there should be no problem setting us down on the peak here.
So these are our remote avalanche control system exploders. This is one of our key solutions to keeping the road open from avalanches. This here is the #1 exploder within our remote avalanche control system up here at the top of Blowdown Peak.
These huge spouts are the latest in avalanche management technology, known to Jeff and his team simply as exploders.
So what this does is sends a directional shockwave onto the slope. There's no actual projectile that will end up on the slope, littering the slope or anything like that. It's literally just a shockwave that stresses the snow and initiates the avalanche.
Huge metal tube-like structures called exploders are installed permanently into the mountain face. And not far away is a shelter housing canisters of oxygen and propane. Through a series of pipes, these exploders are fed a mixture of the two gases, which, once combined in the tube, are ignited by a spark. The resulting blast is expelled at great force out of the directional nozzle onto the snowpack. And if the conditions are right, this will initiate the snowslide. Now the team are able to set off explosions from much further away than an avalauncher. By using radio communication, they can retreat to an extraordinary 25-kilometer distance.
Okay, connecting to the west rib. Fire in the hole.
When the risk is highest, the team temporarily closes the road and an avalanche is triggered. They can then clear the debris and reopen the road quickly and safely.
Having this technology at our disposal definitely does save lives. It allows us to bring down the avalanches when we have closed the road rather than avalanches coming down and hitting the traveling public on the highway.
But runaway snow is not the only potential deadly hazard. What happens when all that snow melts? Danger lurks in one of Whistler's most picturesque locations.
This is beautiful Fitzsimmons Creek. This area was glaciated up until 10,000 years ago. The glaciers melted and they left a landscape littered with debris, and it was poorly forested at that time.
Mike Curry is part of the team tasked with protecting the town from the potential devastation a flood through here could cause.
We have these events that come down the creek that are akin to channelized landslides, or we call them debris floods or sometimes debris flows. If we had such an event, if we were to look up the creek, you'd probably see a frontal wave coming down with big boulders and trees, and it would be kind of coming like a bulldozer down the channel, like a small landslide. And in behind it would be a very turbulent, rocky flow with boulders and logs sticking out of it. It would be chaos.
A debris flood on this scale could rip through the town below. So Mike and his team have devised an epic engineering solution.
So this is the Fitzsimmons Creek debris barrier, the largest of its type in British Columbia. We're way above the creek here, as you can see, and you get a better appreciation for the size of these steel members here. They're very, very large. And the way the structure works is that the boulders and trees that can come down from the creek, they hit the steel pieces there, and the load gets transmitted into the two compression pieces on either side. So each one of those steel beams on the left there is a compression beam that is transmitting the load from the creek boulder impact into the abutment over there. And similarly on the other side here, we have a similar situation going directly to bedrock. It's designed that it will bend but not break during that kind of debris flow loading.
Protecting Whistler from a 1 in 2,500 year chance of a debris flood, the suspended steel barricade design is the only one of its type in the world. Perched above the creek, the 8-meter high debris barrier is capable of restraining 34,000 cubic meters of debris.
We have a heavy steel structure here. It's designed to take a hit from a 1 meter size boulder that's moving at 5 meters per second. And they also have to take a 1.5 meter diameter tree that's traveling down with the flood flow and hitting it like a battering ram.
The town can rest easy, safe in the knowledge that the Fitzsimmons Creek debris barrier will protect them if ever an extreme debris flood should occur.
When it's raining in Whistler and I'm visiting, as I often do, I definitely sleep better in my hotel bed at night knowing that the structure is here.
The Whistler region's most famous and popular peaks are Whistler Mountain itself and the neighbouring Blackcomb Mountain. More than 6 kilometres apart as the crow flies, getting from one peak to another could mean a long and time-consuming journey. But engineers have come up with an extraordinary solution. The peak-to-peak gondola. A world record-breaking piece of mountain engineering.
Be very careful and do not cross these lines.
Wayne Wiltsey has the job of looking after this mechanical giant.
So right now we're at the exit of the Whistler terminal and the cabins are heading off towards Blackcomb.
The peak-to-peak spans 4.4 kilometres, nearly 4 times the length of the Sydney Harbour Bridge. At its highest point, it is 436 metres above the ground. That's almost enough space to fit the entire Empire State Building. To achieve this groundbreaking piece of engineering, 4 giant towers were constructed on the sides of the valley. And on each peak, they built a station containing enough engineering might to pull 28 gondolas, each containing 28 people, across a more than 4-kilometre gap.
That's the main drive bow wheel. These 2 wheels are guides. And why they have the 3 is to spread everything out so that we can get the large gauge that's required for the big cabin. Because of the size of the lift, we have emergency brakes or bow wheel brakes on all 3 wheels.
It would take a 2-year build to create the longest unsupported span aerial ropeway in the world.
So right now we're in the Whistler terminal, the peak to peak. It's prior to public operation. We're gonna take off and we're gonna run across probably at about 6 meters a second. It'll take us about 15 minutes to make the journey across to Blackcomb.
Most cable cars carry their cabins on a single moving cable. This haul rope is supported by a series of towers and loops around the drive wheel at each end of the journey. But take away the towers, and the cable is straight away put under extra stress. And in Whistler, the team are attempting to go further than ever before.
We're spanning the distance between 2 mountains. With one cable, with just a haul rope, it wouldn't be possible because the haul rope would not be able to support the load of the cabins.
The engineer's solution was a 3-cable system on an unheard of scale. Cables, each weighing around 90 tons, were produced in Europe and brought to site using specialist heavy lift transport. It took 11 weeks to stretch the cables across the valley. Each cabin runs on wheels along 2 static cables, pulled by a 3rd moving cable that operates in an enormous 9-kilometre loop. The 2 highly tensioned static tramway cables provide strength and stability in powerful mountain winds.
You know, think of them as tracks. Think of them as a railway, right? So those tracks support and the cabins ride on the tracks, and the haul rope, which runs down the middle, pulls the cabins on the tracks from terminal to terminal. They were able to, with the track ropes, achieve the huge span. So the span between towers 2 and 3 is just over 3 kilometers in length. At the time, the longest unsupported span in the world.
The result is mountain engineering on an epic scale. A unique achievement in construction once thought impossible.
When you go and you actually look through the floor or you look out the windows, it's kind of like flying in an airplane or in a helicopter. It's a pretty cool experience. There aren't any lifts like this in the world.
Building anywhere in Whistler means overcoming a host of extreme natural obstacles, even in the valley below.
Whistler has among the highest snow loads in the country, a country that sees a lot of snow to begin with.
Eric Karsh is one of the team behind building the Ordain Art Museum, a huge new building that will need to cope with 7 meters of heavy snow each winter.
If you ignore the amount of snow that we have here, structurally, of course, it could collapse. Victoria, not far from here, was a town where we had a snowfall that exceeded expectation, and a number of buildings actually did collapse. From the point of view of snow masses freezing and thawing and expanding as it freezes, could literally split buildings in half if you don't account for it. So, yes, it's a somewhat dangerous environment.
So how do you create a building that can withstand the full force of Whistler's snowfall? It's a challenge that might be impossible without the great pioneers of the past. Mount Hood, Oregon. A permanently snow-covered peak blighted by blizzards. How anyone can construct a building to withstand this wild environment is mind-boggling. But structural engineer Nathan Ingrafia is searching through the whiteout for the answer.
We're up above 6,000 feet up the side of Mount Hood. Visibility is maybe 100 yards. It's a really formidable, hostile environment. It makes a snowcat about the only way for us to get around. We're getting close. So this area of Mount Hood, it's not unusual to get upwards of 20 feet of snow in a season, maybe 30. That's plenty of snow to easily collapse your typical roof structure. So you can imagine that designing a structure in these conditions is incredibly difficult.
Daring to build in this most unforgiving of locations was prominent architect Gilbert Stanley Underwood. His mission was to erect a hotel to withstand the impact of devastating snowstorms.
And Matt, you can stop here. It's a good view.
What he came up with was the stunning Timberline Lodge. One of the most extraordinary and unmistakable hotels in the world.
This building has a really iconic shape, especially looking at it from the outside here, from the snowcat. It's really, really a unique design.
Immortalized as the facade of the menacing Outlook Hotel in Stanley Kubrick's film The Shining, Timberline is instantly recognizable thanks to its unique roofline.
The space above me is created by the main exterior structural roof, which is used to shed the snow. It's a tight squeeze.
Just like in Whistler, Underwood needed to create a large building with lots of open public areas that could handle the heavy snowfall.
This is an incredible space to be in.
The answer was a roof design called a cat slide.
So this model represents your typical steeply sloped roof, just to demonstrate how effective this steep roof is at shedding snow. So you can see that this roof is very, very effective at shedding the snow. Now, if you wanted to make the building larger, to compensate for that, you would lower the pitch of the roof. So you can see with this shallower pitched roof that the roof collapsed under the weight of the snow that didn't easily shed off the roof. The way to solve this problem is the cat slide roof. To do this, we're going to have to lose a little bit of the upper floor area. And now using a cat slide roof, the roof extends past this initial eave height all the way down to a second floor, if you will. Now using another identical bucket, you can see that that roof effectively shed all of the snow and no snow at all stayed on the roof. all of that snow that's shed off is now piled up just outside the building.
The ambitious 55,000 square foot Timberline Lodge finished construction in 1938. And its iconic cat-slide roofs were the perfect solution to eliminating serious snow loads.
The concept is somewhat ingenious because it allows you to shed snow while also maintaining as much floor area as possible. Perhaps the only disadvantage here is that we no longer have the view out the window that we might have otherwise, but we've preserved the structural safety of the roof.
Just like the Timberline Lodge in Oregon, it is the Art Museum's clever roof structure that protects it against Whistler's crushing, destructive snow.
So we decided to have this really steep roof and a slippery metal roofing that allows the snow to slip and shed. And as you can see right now, there's no snow at all on the roof.
Like the hotel on Mount Hood, the roofline continues much further than in a traditional building.
That, from a volume design point of view, gives us a space in the middle of the volume that is quite high, where we can have a two-story space. And if you extend the roof beyond that two-story space, you end up with a one-story volume, which is the corridor that we're walking through right now, with a beautiful view to the forest. This way, you can maximize your floor area within that design. So we're in the mechanical well, which gives us a view of the roof from above. So if you look at the roof surface from the top to the bottom, you don't see any joints in the metal elements, which allows the snow to slip off unobstructed because the sheet metal is completely continuous from one end of the roof to the other.
The result is a cutting-edge art museum that can withstand 7 meters of annual snowfall.
It's been my most challenging and exciting project. To build in a town like Whistler, you can't be afraid of challenges. It's not the easiest place to build, but these challenges certainly made it an exciting project.
Our company exclusively works in remote locations. We work all over Western Canada in some of the most rugged, extreme environments that exist. And this pretty much scores at the top of the list for challenging sites.
Ryan Foster is one of the team that must conquer the mountain.
You know, we need to look at this and say, okay, how do we build a structure in this environment? This location is one of a kind. It's almost like standing on top of a pyramid.
The Cloudraker Sky Bridge and Raven's Eye viewing platform will be 2,200 meters above sea level. The highest altitude suspension bridge in North America. It's a design that requires tons of steel and concrete placed on the peak with pinpoint accuracy. But out in the wilderness, traditional construction methods are totally impossible. The solution is extreme air power.
So you can see he's coming in with the log.
The massive Kamov Ka-32 helicopter is designed to be a flying crane, capable of lifting extraordinary weights with ease.
He's got a bubble window, he's looking down. He's gonna bring it in and put it exactly where he wants it off the road. And he'll be placing it right now. Now he'll release the grapple, open up the claws with the arms and fly away. Go for another turn. You need to be very precise.
Shane Palmer is in charge of a fleet of these monsters, and they hold the key to building on Whistler's mountaintop.
So the helicopter's gonna be landing shortly. They're almost down to a fuel level where they have to refuel. I can feel the power right now.
The secret of its lifting power is the twin set of rotors.
The intake there of the engines are 2,200 horsepower right there. 44 altogether. The top set is going one way and the bottom set's going another way. So they have counter torque. That's why they don't need a tail rotor. The way you yaw is they change the pitch of the top set differentially from the bottom set.
The two counter-rotating sets of rotors means the Kamov doesn't need a tail rotor to stop the helicopter body from spinning. So every single horsepower is dedicated to lift.
Hang on. Get a thumbs up there. Everything's looking good.
The Kamov can lift up to 5 metric tons in one go, making it the perfect machine for an impossible challenge. Like building the highest altitude suspension bridge in North America.
So when we're erecting this steel, we are 100% working at height. There are 1,703 pieces of steel to connect. These are extremely heavy pieces of steel.
In Whistler, the Kamov and other heavy lift helicopters allow engineers to build at almost 2,200 meters above sea level.
There's over 95,000 kilos of structural steel, reinforcing steel, and anchor bars. And so that requires a lot of foresight and a very careful plan.
The result is record-breaking mountain engineering. The 130-meter Cloudraker Sky Bridge and the Raven's Eye viewing platform.
It seemed like an impossible endeavor. Incredible piece of engineering that's gone into this. Walking out there, the bridge is an incredible experience to walk through with the metal grate so you can see through to the Whistler Bowl below. And then getting out onto that cantilever, I mean, you're sitting out 13.5 meters off of the rock, off the cliff face, and looking down into snow and ice. It's an incredible experience.
While many of the challenges facing engineers in Whistler are to do with too much snow, sometimes the problem is down to not having enough.
You know, we have a pretty amazing area that we live in. Lots of steep slopes. Whistler's renowned for its steep slopes. And everybody, as they're skiing it through the day, they push the snow downhill, they push it to the side, and they build huge moguls.
The uneven movement of the snow can spell danger. Ramps can form and rocks can become exposed. The obvious solution is to use a snowcat to push the snow to where it's needed. But some of Whistler's slopes are so steep that an ordinary snowcat would end up sliding off the mountainside.
Oh yeah, it's a battle against gravity. Maintaining slopes this steep is a challenging job.
On Vancouver Island, off Canada's west coast, mechanical engineer Agnes d'Entremont is searching amongst the remains of the once booming logging industry for one of the last surviving examples of an innovation that could help the team in Whistler.
This is a temperate rainforest that grows some of the largest trees in the world: Douglas fir, Sitka spruce, western red cedar. These trees were used for millennia by First Nations, but logging really got into gear when Europeans arrived, who built mills like this to process the logs into lumber. The challenge was getting those logs out of the forest, off the slopes, in order to bring them here to be processed.
Moving monster trees required a monster machine. This is a steam donkey. A mechanical beast of burden with unprecedented power.
This is so rare.
Invented by logging entrepreneur John Dolbear in 1881, this steam-powered winch needed a skilled team to operate it.
Grab a chuck of wood there and chuck it in the fire.
Okay.
The donkey puncher running the engine.
Yeah, there you go.
The spark chaser to put out fires.
Wow, you can feel how hot this is.
And the whistle punk relaying signals to the choke setters who attach the logs.
There you go. There.
Together, they could tackle jobs previously thought impossible.
Off we go, Joe. So right now, the logs are being lifted and dragged at the same time by the steam donkey.
But the steam donkey had a perhaps even more extraordinary skill. One that could hold the key to taming the snow slopes in Whistler.
It's incredible that a nearly 100-year-old machine can haul all of these logs. That's not all it can do. It can also haul itself, including to steeper and steeper slopes. And so to do that, they attach the cable around a distant tree and use the winch to haul this giant iron machine on these enormous wooden sleds up the slope.
Using the muscle of the winch allowed the steam donkey to go where no machine had gone before, transforming the logging industry and taming the forest slopes.
This is the office, and it never really gets old.
On the treacherous snow slopes of Whistler, it's modern winch power that holds the key.
Okay, away we go.
This is the Winch Cat. A snowcat with an added hydraulic winch on a 360-degree turret. It's the ultimate off-road vehicle.
If we didn't have the winch, we'd probably do it about 50 or 60 kilometers an hour about now. Like, we'd be going really fast. Conditions like this, there's just not enough traction to hold up the machine. The snow would just shear off and you'd slide.
A steel cable over a kilometre long allows the vehicle to virtually dangle down extreme slopes and move snow exactly where the operator wants it.
Like right now, I have 3 tons of tension holding us back. The technology and what it enables you to do with the machine, it's quite something. What we have to do here, you can see that there's rock showing in the slope that has to be repaired. The boom is now over the cab, which is why it had that shape, so that we can see the rope in front of us as we're going uphill. So right now we're about 700 meters from where we hooked up the rope. You can see the rope in front of us way up in the air. And we are at 29.3 degrees. Pretty incredible, actually. The tracks are starting to slip now. This is a job that would be impossible with a regular snowcat.
Whistler might be one of the most challenging environments on the planet, but engineers refuse to let this world of snow and ice beat them.
You're missing out if you don't take at least one moment every day and do a 360, as this is extremely special.
It's a real privilege to be able to work with this type of technology. It's really spectacular, and I really enjoy my job.
By standing on the shoulders of history's innovators and adding their own imagination, determination, and daring, they are taking mountain engineering to unprecedented heights.
You know, if we didn't have this technology and this engineering in place today, we wouldn't all be up here enjoying the mountains. We'd be in the valley looking up going, wow, I wish I could be up there.
And making the impossible possible. King County, Washington State. Home to Seattle and Bellevue, hubs for the USA's booming tech industry. Where population is exploding and traffic is gridlocked. Engineer John Slavin lives and works in a city pushed to breaking point.
Seattle's experiencing some of its rapidest growth since the gold rush back in the 1800s. We've had more tower cranes in Seattle than any city in the country for a number of years running. With a lot of major corporations in Seattle, the traffic's getting worse, the need for transportation is increasing, and the need for choices are increasing.
The solution could be to link the cities by train. But in King County's unique environment, even railways face a problem.
One of the unique features of Seattle is its geographic terrain. There are a number of lakes that all restrict where and how you can place transportation services. And in particular, Lake Washington sits between downtown Seattle and Bellevue, both of which are high-tech areas that need to be connected.
In a landscape strewn with vast bodies of water, Lake Washington is the largest and deepest. Here, traditional bridges just aren't possible. When it comes to water, cars and trains are stopped in their tracks. Indigenous people used canoes to get around Lake Washington for thousands of years. 19th century settlers used ferries, bringing in so many boats that they became known as the Mosquito Fleet, clogging up the waterways. A more practical solution was required. But with almost 2.5 kilometers to cross and water and soft silt over 100 meters deep, neither a traditional bridge nor a tunnel could solve the problem. But engineers in Seattle have the answer. This once impassable lake has now been conquered by the incredible I-90 floating bridges. A concrete megastructure that actually sits on the surface of the water unsupported by columns.
There's a lot of engineering that went into this to make this all happen, and it's pretty cool to work on.
This project is incredibly unusual in that we're applying systems that has not been done by anybody else in the world ever before. The engineering behind this project is mind-blowing.
These extraordinary buoyant bridges are capable of carrying 142,000 cars a day. But now they're entering the next and most challenging phase of construction. Adding a state-of-the-art train line and creating the planet's only floating railway bridge.
What makes this project so exciting for me is nowhere else in the world has this ever been done. It's floating, it moves. We're essentially putting rail on a marine vessel. It's a very unique engineering achievement.
With a massive 324,000 tons of reinforced concrete, the twin floating bridges weigh more than 52,000 elephants. All that weight is floating on 38 monster pontoons, with nothing but 64 meters of water below the surface. Crossing a span of nearly 2.5 kilometers and capable of supporting the weight of high-occupancy rush-hour traffic. The finishing touch will be a revolutionary railway line, a world first on a floating bridge.
Once this system is commissioned and in operation, this will be an engineering feat like no other.
But this ambitious project poses huge engineering challenges. How do you connect a railway from land onto a floating and so moving bridge?
If those rails were just attached on either side, that continuous connection would experience all those movements in one point and would probably snap the rail.
What happens when you introduce a high voltage current to a structure in water?
There is a risk of stray current escaping from the rails, which could get into the critical bridge structure.
And how do you make it strong enough to support 300-ton trains?
We can eccentrically load the bridge and potentially crack it. That would not be good.
But the biggest problem of all, how to keep the concrete superstructure afloat.
It is very important that if there's any water intrusion, it won't sink the whole bridge.
Engineer Jim Stonecipher knows all too well the daunting complications of building on this lake.
The lake is steep, and being in earthquake country, we need a good material to set our foundations in, and it's just not available on the bottom of Lake Washington. Before you can get to some good material, you have to go through silty sand, and so you might end up with a column that's 500 feet deep.
Even if engineers were to sink support columns through 65 meters of water, they would hit a soft lake bed made of silt and clay. Pillars would need to go through another 50 meters of sediment to reach a solid footing. Add the column length needed above the water, and all this makes for an incredibly expensive and unstable structure.
On the engineering side, it would be difficult to build a standard cable stay or other type of bridge in that area. It takes a unique kind of bridge span to span Lake Washington.
So the engineers' only option is to float the bridges. But how can they ensure the giant concrete structure doesn't sink? The answer lies with a pioneering innovation of the past. On the Caribbean island of Curacao, local engineer Albert Zweste is exploring how a clever piece of engineering could help the team at Lake Washington.
We are located here close to Panama, where they have the Panama Canal. So the island is strategically located for the shipping routes and for trade.
The island's main town, Willemstad, was a perfect port. But by the mid-1800s, the deep natural harbour was creating a problem.
The town is separated in two halves, but about 4,000 people per day needed to get across, and they did it in small boats. And you can imagine it was time-consuming and not efficient process.
But the channel is 150 meters wide and 15 meters deep, with a soft sandy seabed, making most bridges impossible to build, especially one that allows the passage of ships into the harbour.
Okay, here we have the two sides of the town. I'm going to show you now the options that we have to construct a bridge between them. The first one would be a beam bridge. It's a cheap and easy bridge to build. We can put it across and people can walk over to the other side of town. The only thing is, traffic could not go in and out. I have a boat here, needs to go to the harbor, cannot come in. Also, I need a lot of support and the sea bottom is soft, so we'll grab another one. The arch bridge solves the problem for vessels coming in, but only small vessels. An arch bridge would be expensive to create the arch and to make it high enough for larger vessels to come in. The bascule bridge is an option that gives us the possibility to open it and let traffic go in and outside the harbor. It doesn't need to be that high. So we can pull on this, open it up, and my vessel can go in or out. The problem with the bridge is, though, I need heavy foundations in a town that's already been built in a deep channel with soft foundations. So this bridge, although beautiful, is not an option for this site.
But when American ice merchant Leonard Burlington Smith sailed into Curacao in 1876, he had the answer.
So this is what Smith came up with. This is the Queen Emma Bridge, a wooden pontoon bridge with 17 pontoons stretching across this channel, the Anna Bay.
Affectionately known to the locals as the Swinging Old Lady, it's one of the oldest pontoon bridges in existence.
This bridge uses about 600 tons of wood. Each pontoon, 15 tons of steel. You see it moving? We are now completely floating on the water.
But the brilliant pontoon design not only allows for transit between each side, the floating bridge has another trick up its sleeve.
We've got a boat coming now, so we need to open the bridge all the way up to let this boat get out to sea.
The impressive 167-meter bridge span is hinged at one corner and swings open, allowing boats access to the harbour.
To be able to open the bridge, we have two motors, one in forward, one in reverse. Together they push and open the bridge. We get oil tankers, we get container vessels, we get cruise vessels come in here, all kinds of vessels. It was genius. It was a quick solution, an efficient solution, and a relatively cheap solution.
Smith's design was brilliant in its simplicity. Located just beneath the public concourse lies the vital components that will prove significant to the engineers of Seattle.
Okay, we're here on one of the pontoons. The pontoons are the most important feature of the bridge. All this weight is carried by the pontoons. No columns are needed to anchor this bridge into the sea bottom. Now you can see that the bridge has more than one pontoon. This is to displace the weight, of course, and the length of the bridge, but also the pontoons give us redundancy. If one gets damaged, it can be removed and can be replaced by another. When it's removed, the other pontoons will carry the weight.
Pontoon bridges may have been around for millennia, but few have lasted quite like the swinging old lady.
Walking on this bridge, it's an amazing feeling, and it gives me goosebumps every time that I walk over it and every time that I see it open.
On Lake Washington, engineers have taken the idea of the pontoon bridge and supersized it. The pontoons in the enormous I-90 floating bridges are large enough to support a highway with over 50 million cars a year, and a new railway, the first of its kind on the planet. Tasked with maintaining the bridge, engineer Jim Stonecipher is heading out to take a closer look.
So our solution to crossing Lake Washington was building these pontoon bridges. We make a concrete pontoon out of very dense concrete with hollow cavities inside. The concrete has enough buoyancy in it to support the bridge and the traffic on it.
During construction, 38 giant pontoons are positioned end to end, giving the illusion of one colossal bridge base. Each pontoon is divided into cells and sealed with watertight hatches. 2 overhanging bridge decks provide enough space for 8 lanes of traffic and 2 train tracks.
One of the reasons we have so many pontoons is for redundancy, so that if one fails, it won't sink the whole bridge. Each compartment has its own door and sealed off, kind of like a ship. And that way, we don't lose a pontoon bridge and we can maintain traffic.
Keeping these mega bridges afloat is an impressive feat. But with no fixed footing, it takes more remarkable engineering to stop them floating away.
Down below us, you're going to see the anchor cables that help stabilize the bridge and keep them in place. And here comes one now. You can see them just below the water. The longest anchor cable is about 739 feet in about 165 feet of water.
Buried in the lake bed, movements from the bridges put immense pressure on these anchor cables, causing them to fray.
No, I got a cable here.
So, to prevent catastrophe, a team of divers working at depths of up to 165 feet are currently replacing damaged components.
The anchor cables are very heavy, and it takes a real big team to get those anchor cables in place.
So far, 32 huge new cables have been installed. But seasonal change means that monitoring them is essential.
From summer to winter here on Lake Washington, as the lake raises and lowers, the anchor cables become slack or tight. And we don't want increased pressure on the bridge, or we do not want the cables to be slack.
A rupture in the cables could spell disaster for the bridge. So it's crucial that, as the lake's water levels change, the anchor cables are adjusted to the correct tension.
So now we're down inside of one of 18 pontoons. Watch your head, low rough. We're walking in through the anchor cables in one of the segmented compartments of the pontoon. And this is the anchor cable on the pontoon. This particular anchor cable is 579 feet long.
To haul such an enormous cable in these tight spaces, you need a compact yet powerful piece of equipment.
So this is the jack that we use to actually make the adjustment. This is a 150-ton ram. We use this to either extend the cable out a little bit or bring the cable in to maintain a 65-ton average on the cable.
The jack pulls with phenomenal force, but all Jim has to do is press a button.
So you can see the travel of the cylinder right there. We're actually very slowly pulling the cable in. Over here in the other room, you can see we have this air cap between the jacking plate and the jacking head. And so we're actually pulling the cable into the pontoon. So now we've gained about an inch. So we're gonna put shims in here.
These steel plates will bear the load when the jack is released.
Right now, this time of year, we only have to move it probably an inch. In the spring and the fall, we'll move it about 6 inches.
Adjusting the 110 anchoring cables is vital for keeping the bridge in alignment and maintaining a safe road surface for more than 50 million vehicles every year.
So if we didn't have these anchor cables, eventually this bridge would float north or south depending on which way the wind's blowing. End up maybe in somebody's backyard, and that'd be a pretty big dock for them.
Across a combined bridge span of 4.8 kilometers, these 38 jumbo pontoons support a lifeline for millions. Without these incredible floating bridges, the city would be gridlocked. Construction of this groundbreaking project is underway.
To my right is the first set of tracks. There'll be 2 sets of tracks here when the construction is complete.
But the new tracks create a unique danger that engineer Craig Dalala must overcome.
The rail system is powered by a 1500 volt DC system. The return path for that current is the rails here. Nowhere has anybody put a 1500 volt rail system on a floating bridge in the middle of a lake.
But water and electricity famously don't make a good mix. If electricity escapes the tracks, it could spell disaster for the bridge. Surprisingly, the danger isn't one of electrocution, but of corrosion.
So anytime you have a steel structure, the risk of rust or corrosion, which is the loss of metal, could impact the bridge. By introducing rail to the floating bridge, it further increases the risk of corrosion to the bridge and the bridge structure.
When that current discharges into the water, it can corrode crucial components at the exit point, threatening the integrity of the very bridge itself. For this world-first construction project, Craig's team needed to come up with entirely new methods to eliminate destructive stray current.
So you'll see here that there's multiple elements of isolation, including plastic pieces here between the track and the fastener. We also coat the bridge with a special dielectric material that is also a high insulator for electricity. And so with these elements, we are able to protect the bridge from any stray current ever making its way onto the bridge.
But with this mighty structure at stake, engineers aren't taking any risks.
To move these barriers out of the way.
Should any stray current make it through the first line of defense,
This is going to be harder.
There's a backup plan.
The anode assembly is the one without a tape here.
Okay.
So what we have here is the anode coming out of the water. There's 8 of these that hang 50 feet down into the water. These are mixed metal oxide anode assemblies. These put current into the water, which is drawn into the bridge and allows the bridge to polarize.
Left unchecked, stray current could enter the lake through bridge metal. But over 1,400 anodes feed another electrical charge into the water. This protective flow drives into the bridge structure and holds the stray current at bay, saving crucial components.
Without corrosion control, the life expectancy of the bridge could be shortened. Applying it to a floating bridge like this is really something extraordinary.
The danger of corrosion has been eliminated. But as rail installation advances, an entirely new threat looms over the project.
So right now we're about to go across the bridge.
Keeping the mission on track is engineer John Slavin.
As we transition to a floating bridge, we are on a floating structure. And just like any marine vessel, it tends to move a little. Now for an automobile with rubber tires, they can go across an angle point or a bump quite easily. And this is very difficult for a train because steel rails need to be continuous. They can't have break points or angle points that could potentially disrail a train.
The floating bridge needs to contend with a range of movement caused by lake levels, wind, and uneven traffic loading. This stretching and twisting at the joints constantly changes the transition angle, threatening a track misalignment between lake and land. For 800 passengers on a speeding train close to heavy traffic and deep water, this could be fatal.
We need to find a solution across that expansion joint that's critical to the operation of the rail.
To evade a devastating derailment, John's team must connect with innovators of the past. Norway, famed for its vast fjords. Civil engineer Bertha Dongmo Engeland is on the hunt for a relic from the golden age of locomotive travel.
In the beginning of the 20th century, the quickest and most efficient way for factory to export their goods was by train. The only problem is to get access to the railway line. Those factories are located on the wrong side of the lake, and train doesn't float.
Scottish engineer Thomas Bush encountered a similar problem when extending Great Britain's railway lines. But in 1849, he came up with a solution that would roll out across the continent. The railway ferry.
Wow, look at that. This is so amazing.
Bush's concept of a ship with inset rails enables locomotive wagons to float across water.
This ferry here in Norway follows closely Bush's design. When railway ferry came here in 1909, it was a wonderful opportunity for the factories to export their goods by rail, and we are lucky enough to see it today.
But the ferry itself is only part of the story. Once the wagons have reached the end of the line on land, there's still the problem of getting them onto the barge.
This is the most delicate part of the operation. It's very important that the boat and the pier are at the same level.
A misalignment of the track would be catastrophic. And with lake water levels constantly changing, Bush needed a clever solution.
I have my miniature lake here, and the water level is low. And we have a gap here that can cause some problems for our train. So basically, we need to find a way to connect those two tracks together. The solution to this problem here is to use a hinge ramp that can move and allows us to establish a connection between the dry land and the floating barge. And our train can now smoothly transition from dry land to the floating part. And the most important part here is that the hinge allows us to change the angle so that we can accommodate any water level. It's simple, but brilliant.
The adaptability of Boucher's hinged ramp is a concept that will prove instrumental for the team in Seattle.
So we are going to bring the ramp down and connect it to the ferry now.
With the help of an enormous winch system, the span is lowered and tracks perfectly aligned.
This transition ramp, starting exactly here, is hinged on one side, so that we can lower it or raise it, so we can always have this perfect alignment with the ferry.
Connecting these tracks provided a lifeline for the region's industry, with an astonishing roll-on, roll-off solution.
It's impressive. It's really cool to see this.
The remarkable railway ferry and hinged ramp configuration kept cargo wagons on the move and changed European locomotive transportation forever.
This innovative concept was a game changer. Train doesn't float, but vast lakes and fjords like this one were no longer an obstacle. And it's quite amazing to see that design still in action 100 years later.
A 170 years after Boucher's inspired idea, Seattle's greatest engineering minds have developed a system that he could have only dreamed of.
And so this is our solution. We call this a track bridge because we're bridging over that expansion joint. And it's an amazing, actually, solution that we came up with.
This unique design has to deal with conditions not seen on any other railway bridge in the world.
We had looked at some other systems, but this has 2 more degrees of motion that don't exist on other bridges. What we have is a system to try to handle all those different levels of movement, but rather than happening in one point on the rail, we've spread that over a longer distance. And how have we done that? Through a lot of components. As we go underneath here, we can see some different elements. Each of these wings have a curve to them. That means when the bridge goes down, because the lake level goes down, these wings will rotate up. And when the opposite happens, these wings rotate down.
These curved wings work in unison with a complex range of components to bend the rails into a gentle arc and keep them level over the moving angle points. 8 of these 13-meter-long track bridges will cross the 4 hinges between fixed and floating segments, allowing a smooth transition for the trains. After the complex track bridges are assembled, the system has to undergo extreme scrutiny to ensure safety, speed, and efficiency. So they're thoroughly tested at a special facility in Colorado, producing 500 channels of data.
Our test revealed that at our design speed, our maximum speed of 55 miles an hour, the track bridges were good, the stresses in the rails were fine, and the ride for the passengers was comfortable. If we didn't have this track bridge, it probably would have been impossible to put trains across the bridge. At the very least, we would have had to stop the trains and almost just bounce across it. At its worst condition, that may have even caused the trains to derail at that low speed.
With this incredible world-first design, Seattle's engineers are one step closer to conquering the seemingly impossible.
This is a completely new and unique solution addressed just for this specific location. Nowhere else in the world are there any track bridges like this. We have thousands of daily commuters that rely on this, as well as sports fans and university students.
Engineer John Slavin is in charge of the project.
So when these trains are fully loaded, we'll have 4-car trains, and each car will weigh approximately 175,000 pounds. So when 2 trains are passing each other and essentially doubling the load, which is very heavy in one spot, that puts a lot of stress on the concrete.
A massive 4-carriage train at maximum capacity could weigh 350 tons. When 2 trains pass, that's as much as 700 tons bearing down on a short stretch of bridge. This crushing load can put enough stress on the concrete to cause catastrophic ruptures.
We've done a lot of structural analysis on these loads and realizing it takes a lot of stress into the bridge. And so to preserve the lifetime, we need to figure out how to strengthen the bridge.
So how do you reinforce the concrete to withstand the full force of hundreds of daily train crossings? It's a challenge that might be impossible without the innovators of the past. The city of Lourdes, southern France. An important holy site for Catholic pilgrims from around the world. Civil engineer Patrick Nagel is going underground in search of a structure with the capacity for a colossal congregation.
Wow.
This is the Basilica of Saint-Pieu-d'Y.
I'm completely awestruck by this building. It really is impressive.
It's built beneath the city to protect views of the sacred site above ground.
What is striking about this magnificent building is a wide open space. No central columns, no supports. And we can see the structural form of the 29 arches running the length of the building. And this creates a usable space of over 10,000 square meters, which can accommodate 25,000 people.
But this subterranean structure seems to defy gravity.
The flatness of the arches is maybe something we wouldn't expect. A typical arch is much more like this. These are very flat arches. It is clear that something special here is happening from an engineering perspective.
Engineering enlightenment came from Eugene Freycinet. In 1928, he perfected a method of concrete strengthening using strands of steel cable under high tension. This technique, known as post-tensioning, provided support for concrete beams of unprecedented spans. But hidden within the concrete, it's not easy to see how this system works.
So here we have a simple model. We have a number of wooden blocks which represent a concrete beam resting on 2 supports. And you will see a string running through the beams, which is simply there to hold together the blocks. If I apply a load to the beam, you will see that it is put into bending, and you can see cracks opening up within the concrete. So the secret is to put in compression before the load is applied.
To achieve the compression needed, post-tensioning must be introduced into the beam.
So in this case, it is provided by string and a tourniquet to tension the string. So I have now tightened up the stressing, if you like, and we put this back on the supports. So this time we can apply double the load, and we can see that there is no movement and the beam does not go into bending. This gives a much more efficient use of the concrete and allows us to provide bigger spans and more efficient use of the material.
By compressing the beam, its density and strength is increased, a method that could prove vital for Seattle's bridge engineers.
So essentially what we are doing in the beams, in the arches behind me here, is applying an external force to increase the load-bearing capacity of the structure. The tendons that we see in here are formed of steel strands housed within ducts and stressed by hydraulic jacks after the concrete is hardened.
The strengthened concrete provides a vast ceiling without the need for obstructive pillars. Instead, arches span the chamber and descend to the floor close to the edge.
Looking at the structure today, there are no cracks. It is very finely designed to make sure we maximize the capacity of the concrete.
The long, shallow vault of this hall would not have been possible without Freycinet's miraculous post-tensioning solution.
Today, we see it used in all major structures, bridges, buildings, dams, and without it, we would not be able to achieve some of the beautiful and brilliant structures we see around us today.
At Seattle's floating bridges, engineers are applying Freycinet's groundbreaking technique on a world-beating scale. Just like at the Basilica, they're fortifying concrete through extreme compression.
So what we've done to strengthen the bridge is put post-tensioning cables in the bridge.
But the supersized system on Lake Washington is using some of the longest post-tensioning cables the world has ever seen.
So these cables are approximately 4,000 feet long, running from one end to the other, one continuous cable in each one of these conduits. Very unique in this situation that we've added 4,000 feet of post-tensioning. Most post-tensioning is much shorter, 100 to maybe 200 feet.
With a combined length of 24,000 meters, 20 of these steel super cables are thread through the pontoons, spanning the North Bridge's floating platform. Powerful hydraulic jacks then pull them tight with immense force.
So what we've done is we've put conduits through the bridge. Those conduits are then used to string the cables through that, and when we pull those cables tight.
But keeping a post-tensioned monster cable in place requires oversized anchors.
So here are the reaction frames inside the bridge. These are the big steel frames that we pull tight against when we tension the post-tensioning cables. So their job is to hold the post-tensioning cables tight so that we put that force into the bridge to strengthen it.
20 massive reaction frames weighing 7.5 tons each are pulled inwards by the tensioned cables. Like huge bookends, they squeeze the bridge from either side. Compressing the concrete increases its density, and so strengthens the bridge to take an even mightier load. Applying extreme compression to the structure has to be executed with pinpoint precision, to within 1.5 millimeters.
These frames are critical. Without them, there's no way we could have added post-tensioning.
The result is a super strong floating platform capable of withstanding the 700-ton point load of 2 trains crossing simultaneously.
So this is an incredible solution to the problem. Extremely long post-tensioning cables added to a bridge, allowing us to add the trains to the surface of this bridge.
For the team behind this daring project, the engineering achievement is immeasurable.
The floating bridge is an amazing structure. It's critical to our region.
This is one of the most challenging projects I've ever been involved with. Because of all the unique items, you can't just go take something out of a design handbook. You have to think about how each one individually interacts with each other to make the system as a whole perform well.
This has been a great project, and I can't wait to see it start in service.
The unparalleled twin bridges that have defied the impossible, spanning a previously impassable lake, creating a lifeline for a population of millions. And their brand new crowning glory, stretching thousands of meters from shore to shore, all stand as testament to the incredible work of some of Seattle's greatest engineering minds. The I-90 floating bridges represent impossible engineering on a staggering scale. Every stage of this groundbreaking enterprise poses extraordinary challenges.
There are many facets and many people involved in this design, and it's been really great working on this. I'm really proud to see it coming together.
By building on the work of the pioneers of the past, overcoming huge challenges, and pushing the boundaries of innovation.
This is some of the most incredible engineering that I've ever seen.
It's extremely exciting for me and my team to be able to work on such not only an important project, but a unique project.
The engineers are succeeding in making the impossible possible. The world's oceans contain some of man's most extraordinary engineering achievements. Here, size knows no bounds, and the megastructure is king. Ships, oil rigs, and floating factories are all growing to an unprecedented scale. But these oversized objects present engineers with a giant challenge. What happens when you want to move them? Michel Tsai is one of a team of marine engineers tasked with designing a solution.
The structures for this industry are the biggest in the world that need to be transported. In front of us you can see an oil rig which is operating around the globe and is difficult to move by itself. The cargoes that we have to transport are in some cases 5 times as heavy as this platform. They need to be transported a distance of over 10,000 miles. That's a trip about half around the world. In order to transport these cargoes, we need to build a unique piece of engineering that's bigger and more capable than anything presently available.
It's a challenge that engineers have long been struggling with. It's thought that Neolithic man had to rely on wooden sleds and plenty of people power to help build Stonehenge. The arrival of the railways allowed for the movement of more heavy goods than ever before. But they still have their limits. Ships have the space and strength to move massive weights. But loading a giant cargo usually means taking it to bits. But now, at last, there is a solution. This is the Boka Vanguard, the biggest lifting ship in the world.
This is absolutely a game-changing piece of engineering. She carries some of the largest machinery built on the planet, hundreds of thousands of tons she carries on her back, and she carries it for thousands and thousands of miles.
And the secret to how it does it has to be seen to be believed. The Boka Vanguard can deliberately sink itself. By submerging below the surface, the Vanguard can load cargo of a truly astonishing size.
She's absolutely amazing. Everything on this ship
is different from the standard vessel.
Then the Boka Vanguard does something even more extraordinary. It rises from the depths and plucks its mega cargo from the sea.
It's unbelievable if you start thinking about a vessel like this, that you're actually able to lift cargoes out of the water that are weighing over 100,000 tons or even more.
At 275 meters long and 70 meters wide, the Boka Vanguard is the world's largest heavy lift ship. It has a 12-story superstructure containing the bridge and living quarters. It has 4 28-meter buoyancy towers that can be reconfigured for unique loads. And it can sink 20 meters below the waterline before lifting a record-breaking cargo of up to 110,000 tons. For Captain Oleg Mariasov and the crew, this is a ship like no other.
Okay, gentlemen, on Friday we're going to leave for Singapore. We have to sail through the channel and proceed to the open sea.
To give you a sense of the scope of the size of this vessel, we can carry the Eiffel Tower and the Statue of Liberty at the same time.
Be sure that all life-saving and firefighting equipment is ready for the voyage.
If you look at this vessel, it has a unique design. If you look at the length of the deck, 275 meters, the width, 70 meters, there is no such vessel in the world with this free deck space to carry the largest cargoes in the world.
Before departure, make sure that everything is secured for sea.
Yeah.
So how does the Vanguard achieve the seemingly impossible and deliver the planet's largest cargo around the globe? In order to do so, engineers have had to solve a series of problems. How do you sink and re-emerge at will and lift unprecedented weights?
We had to change our traditional designs and come up with something totally new to move cargoes that no other vessel in the world can move.
How can you maneuver this monster machine through the world's most dangerous seas?
She has to go around the Horn of Africa, which is some of the most treacherous waters on the planet.
And when you're carrying a priceless megastructure, how do you protect yourself from disaster?
So the worst case scenario is damage to the hull of a vessel, flooding of a vessel, and sinking of a vessel.
First mate Rudolf Limanis and the crew are regularly faced with seemingly impossible challenges.
We can see actually an oil rig standing there, and you obviously cannot use any kind of crane for lifting this thing out of the water. It's too big, too heavy. There are no cranes in the world that can lift something as big as this. The other option might be towing. So use tugboats and just tow them wherever they need to be. But it means that it takes a lot longer time for us, and it also might be more dangerous. The weather can be perilous outside, and if this structure like this is being towed, it means that she's out there in any kind of weather. There might be storms or high waves, so this is when the submerging of the vessel comes into play.
But how do you sink and then raise an enormous vessel and its cargo at the flick of a switch? To find a solution, the Vanguard's engineers needed to look to the past. On the shores of the Gulf of Mexico.
Are we ready? Okay, we'll start.
Marine engineer Krijn Hasnoot is rallying his crew ahead of another offshore adventure.
What we basically do is that we install rocks on the seabed. The vessel is 130 meters long, 32 meters wide, and we can take around 11,000 tons of rock.
Today, the Rolling Stone is used in pipe-laying operations, but she has a hidden past.
Everything behind me was not there before the conversion in 1994. From here to the casings, it was all just flat deck.
When it was built in 1979, this ship changed the world. This was the Super Servant 1, the first ever large-scale heavy-lifting ship. Capable of sinking at will, she could lift loads far heavier than anything that had come before. And it holds the key to how the Boka Vanguard works.
The whole deck was empty, so they could take as much cargo as possible. You can see, we put a lot of equipment there, but the structure is still the same. If you know where to look, you can see the structure of the old Super Servant all over the boat.
Ship's first mate Floris Zeilmarker is on the hunt for the telltale signs of historic engineering innovation.
We have a ballast console over here. It's totally original from 1979. This was the first system of its kind in the world. It's totally unique.
By filling 24 huge tanks in her hull with water, the Super Servant was able to sink its deck 6.5 meters below the surface. This allowed cargo to float directly above it. Before the tanks were emptied, buoyancy increased and the payload lifted from the water.
This system allows us to raise and lower the ship easily. By doing it this way, we could load floating equipment without using cranes.
The secret behind this game-changing system lies below deck.
We are now in the ballast compressor room. We still have two of the originally 3 ballast compressors. This allows us to raise and lower the ship in a very efficient way.
The Super Servant's compressors were capable of pumping 2,500 cubic meters of water in and out of the hull every hour, allowing the ship to achieve the seemingly impossible.
This was the first system of its kind in the world. It's truly amazing that even after 40 years, a lot of this technical equipment is still working.
The Super Servant led the way for a new form of heavy-lift ship. Now converted, only a few know its trailblazing past.
We, as a crew, are very proud to work and live on this vessel with such an amazing history. Super Servant was one of the most innovative ships in the world.
The Boka Vanguard is almost 7 times the size of the Super Servant and can lift many times the weight. The largest semi-submersible lift ship ever built.
Yes. Okay, copy that. Start the ballast pump. Thank you.
On board, engineers are able to count on a supersized version of the technology used on the Super Servant.
This is the main console. On these monitors here, we can see all our ballast system, the piping, the pumps. These blocks, they represent our ballast tank. Total 96. Each ballast tank is connected with a valve. And on these screens here, we can open and close the valves as needed. When the valves are open, the water is flowing in.
The Vanguard's 96 ballast tanks can take on more than 200 million litres of water, the equivalent of 80 Olympic swimming pools. This allows her to lift weights larger than any vessel has been capable of before.
So in the beginning, when I start my operation, most of the tanks are empty. We start the pumping water from outside of the vessel through the ballast system that goes all around the vessel.
By deliberately flooding the hull, The Vanguard's deck is submerged to as deep as 20 meters below the surface.
As these tanks are being filled one by one, the vessel is going more and more underwater. And then when we have reached our target draft, we just close the tanks, stop the flow of the water, and then the vessel is in the position.
However, the sinking is only the first phase of this incredible exercise. Superintendent Dom Kemmler is amongst those responsible for manoeuvring the massive floating megastructures above the Vanguard's deck.
The seas, they don't care what your cargo weighs, and they will move it around quite easily. The stakes can be quite high because everything that we're moving is in the hundreds of millions of dollars. And the biggest issue that you have with the largest weights when you've got 100,000 ton cargo is momentum. The faster something is moving, the harder it is to stop it. And if you can't stop it in time, then you run the risk of causing damage to either the cargo or the vessel itself. It needs to be done slow and very steady.
So how do you keep such gigantic structures under careful control? To find the solution to this supersized problem.
See, an elevator would have been much easier.
Whew. Dom is heading for heights that few get to experience on this remarkable vessel.
We're at the top of one of the buoyancy casings. There's very few people get to come up here.
And not only is the view spectacular, this off-limits location holds the key to helping avert disaster.
This is one of our cargo winches. We have 2 of these on every one of these casings. The winches are specifically to pull in a controlled manner the cargo above the deck. We will have this line down on one of our workboats, which will then run the line out and attach to the cargo. Often we find ourselves, especially with this vessel, working with loads anywhere upwards of 110,000 tons. So these winches are capable of putting a tremendous amount of force on these objects and able to move them quite easily through the water.
It's a technique that allows the crew to precisely maneuver the giant structures into position, reducing the risk of collision.
I'm in communications with all the winch operators, and I will say heave up on line 1, and he will heave up on his, or I can give him specific directions, heave up 1 meter, and maybe I'm telling the other winch to slack 1 meter, and that's how we can control it and move really slowly. Every time we do one of these projects or one of these operations, it never ceases to amaze me how impressive and how awe-inspiring it is. We could not do our job without these winches.
Thanks to the Vanguard's system of 96 ballast tanks, 4 buoyancy casings, and 10 winches, she can achieve the near impossible feat of sinking below the surface of the sea and safely moving giant payloads above her deck. It's down to First Mate Rudolf Limanis to oversee lifting the massive cargo from the water.
Everybody stays focused all the time because this is a very huge and high-scale operation. When we look out of this window during the cargo operations, we only see the casings kind of sticking out from the water, and then we see this huge structure. When somebody asks how big is it, I say, well, imagine a 10, 12-story building and let's say 200 meters long. At the final stage of the loading, you just see a wall here of whatever cargo there is.
To finally land the monster payload onto her deck, what goes down must now come up.
The cargoes tend to get bigger and bigger, and every time is like first time. So after the cargo is in position, everything is confirmed, my pumps are running. Then I open the valves to the tanks that I need to deballast. The water is being pumped out from the tanks outside of the vessel. This way, the buoyancy is increased and the vessel comes out of the water.
As the vessel rises, it can lift up to 110,000 tons. But as project manager Ronald Gutierrez knows, when you're carrying a massive megastructure, entering the confined space of a port is a tricky proposition.
Not all ports are happy to receive this vessel, especially not with a large cargo, because it scares them off. It's not a usual vessel, it's not a usual site. And because of these challenges, it's important that this vessel can sail halfway around the world without stopping.
Lead engineer Andriy Kurochkin is charged with maintaining the machinery that makes such voyages possible.
We have two 6-cylinder engine and two 12-cylinder engine. This engine has a 6-cylinder and the output of this one is 4,350 kilowatts. The total power is 26,000 kilowatts.
That's the horsepower equivalent of 8 freight locomotives.
All 4 engines at full speed. We sail with 13 or 14 knots. As a normal routine preparation of the engine, we will do the air blow, and after that we will start the engine. That is to verify that there is no any water accumulation in the cylinders. The cylinders are free of water and there is no any accumulation of oil. So now the engine is ready for starting and we will start the engine locally.
These awesome engines allow the Vanguard to achieve the near impossible on each and every voyage.
Sounds good. The engine is ready for operation. These engines are perfectly doing their job. These 4 engines running. We can easily do the voyage from China to Brazil, non-stop, at full speed, 100,000 tons of cargo on deck.
To complete these global missions, Captain Oleg must maneuver the Vanguard and her payload across the world's most dangerous seas.
Then the vessel carries big and massive cargoes. The windage area is very high and the adverse weather conditions with strong winds, the winds can stop the vessel and swing the vessel. It's like a big sail, and if a wind blows to this sail against, it stops the vessel. But we have a time frame to deliver the cargo from one port to another port. And if we lost speed, we lost time and cannot deliver the cargo in time. So during the operation, the captain must keep everything under control.
Could the answer to keeping the Vanguard moving, whatever the weather, lie with the pioneers of the past? For centuries, boats have relied on a rear-mounted rudder to steer. But without forward motion, the rudder is useless. 17th century battleships had to come broadside to get a clean shot at their opponents. But if the wind died, hitting the target became impossible. And early cruise liners struggled to maneuver in tight confines, so had to rely on expensive tugboats every time they made port. The the River Rhine in Germany. Mechanical engineer Aoife Considine has travelled to this landmark waterway to get her hands on a piece of aquatic engineering history.
Ready for this? This is just incredible! Woo! So you've got 17 tons of vessel here and at 15 metres. I mean, you can just see the weight going out the back. For something 60 years old, this is really, really incredible. The thing even goes backwards. It was the only boat that was able to do this at the time.
In 1963, engineer Josef Becker launched the Forelle. And this pioneering boat was designed to solve a problem.
Now, in a conventional boat system, when you have a separate propeller and rudder, you have to have forward movement and momentum before the boat can actually even start to turn. For a boat such as this, that is 15 metres long and it weighs about 17 tonnes, you are going to have a tough time navigating around tight inlets. It's actually quite difficult to manoeuvre.
What Becker came up with allowed the Forelle to move on the water in a way that had previously been impossible.
He managed to combine both the propulsion of the boat with the manoeuvrability in a 360-degree rudder propeller.
On conventional vessels, thrust and steering are separated, meaning changes in direction are delayed. By integrating rudder and propeller into a single unit, reactions are instantaneous.
The way it works is the engine, which is the main powerhouse, that provides the energy down a drive shaft towards the back of the boat, which then does a 90-degree turn going downwards, a second 90-degree turn, and then that actually leads straight onto the rudder propeller, which provides both your horizontal degree of axis turning for your manoeuvrability and also has the propeller turning at the same time.
Becker's innovative system proved the perfect solution for improving the agility of boats.
Now, to try and do this kind of manoeuvre in a conventional boat, you have the propeller and the rudder both separate, so it isn't that instantaneous movement that we're having right now. And I mean, I'm no boat skipper, but this is actually really, really easy to manoeuvre. So how it actually works, if you look at these gauges here, your arrow's pointing your direction of travel. So, say for instance, we wanted to turn right quite quickly. All we do is turn the wheel twice for 45 degrees, and already you can see the boat is moving. And actually what's happening is as I turn this wheel, the propeller underneath the boat is mimicking that movement and allowing for that instantaneous change of direction. Turn it 2 more times again. And as you can see, the dial is moving with me, which is exactly what's happening with that propeller to be able to push us in this clockwise direction. And it really is just that simple.
The rudder propeller allowed for control and manoeuvrability previously thought impossible.
So let's spin this girl around and see what she's got. It really does just react immediately to what you're doing. The boat is literally spinning on its own axis. Before the invention of the rudder propeller, this really just wasn't feasible with boats.
Becker's invention was so successful, it's now standard on ships around the globe. On the Vanguard, Chief Engineer Andriy Kurochkin has access to a supersized version of Becker's innovative technology.
We are now in one of the unique compartments of the Boka Vanguard. We have on board 2 thrusters, 3,000 kilowatt each.
Manufactured in China, each propeller measures 2.8 meters across and is precisely engineered from copper alloy. The massive props are housed inside a cast steel pod, allowing it to rotate through 360 degrees, just like on Josef Becker's Forelle. But the versions found on the Vanguard have an extra trick up their sleeve.
Once you want to run this thruster, hydraulic power is used to deploy the thrusters from the hull. The gearbox will move down. This will push the propeller and pod out of hull.
Normally stored inside the hull to reduce drag, the Vanguard's rudder propellers are deployed using giant hydraulic rams, capable of turning through a full 360-degree range of motion. They provide the thrust required to counteract wind and waves that could push the ship off course. For Captain Oleg, the rudder propellers are key for maneuvering the Vanguard.
So let's say if wind blows from the starboard sides, the vessel has tendency to go to the port side. To prevent that, we use the thrusters. We turn it to the starboard side and increase the pitch on the propellers. The vessel will go to the starboard side against the wind. They give us additional power and help keep the heading against the winds and waves. Any case of collision is very serious. The worst case scenario is damage to the hull of a vessel, flooding of a vessel, and sinking of a vessel.
To help prevent disaster, the Vanguard's designers must look to the maritime pioneers of the past. In Shanghai in China, Professor Xiao Yingjie is on his way to uncover the secret behind one of the most iconic and influential vessels in maritime history. The Chinese junk.
This is an amazing Chinese boat built for exporting and trading since Tang Dynasty. Very beautiful.
First appearing on the water more than 2,000 years ago, the junk's immediately recognizable spine sails and sleek shape marked a huge step forward in shipbuilding technology. But arguably its most important design feature helped solve a problem that had been plaguing Chinese sailors.
The ships would be offshore for a long period of time. If they are damaged in the storm, the crew will be lost or cargo will be damaged. The ship needs a solution for the safety of crew and the cargo.
Because early vessels had one large compartment below deck, any water that entered would fill the hull and sink the ship. So in order to find an answer, engineers went back to the drawing board.
When they built the ship, the whole part came first. The most clever part came later.
It's a solution that helped redefine maritime engineering for generations and will prove critical to keeping the Boka Vanguard afloat. And the only way to see this hidden innovation is to head below deck.
This is it. Watertight backhand. The idea is to divide the hull into separate parts. The backhand strengthens the ship, reducing the flooding water in emergency.
Dividing the junk into multiple watertight segments offers two crucial benefits. The lateral divides make the hull more rigid, giving greater structural strength. And in the event of a collision, water can only fill one compartment, preventing the ship from sinking. Introduced on the Chinese junk hundreds of years before it caught on in the West, the bulkhead revolutionized shipbuilding.
This is a boat without bulkhead. The problem is when it has emergency. The ship is sink because the whole boat is full of water. And this time, it is a ship with bulkhead. When in the emergency, only one compartment is full of water. But it is safety. This is a very clever design. It is repeated in the history.
The introduction of bulkheads allowed junks to sail the oceans in safety for thousands of years, influencing ships of all shapes and sizes along the way. The Vanguard's engineers have taken the Chinese concept and implemented it on an enormous scale.
There's a lot of awkward spaces down there. It's really tight. So when we climb down, take care not to injure yourself.
Chief Officer Rudolf Lemanis is leading engineer Michel Sai deep below deck to inspect the Vanguard's enormous bulkheads.
Watch your step. It's really slippery and lots of tripping.
It's a location that's hard to reach and few ever get to see.
So you were working on the design, yes?
Yeah.
It's quite high.
Yeah, 10.3.
10.3 meters high.
I still remember the dimensions.
And while this cavernous space is rarely accessed, it's essential to guarantee the safety of the Vanguard in case of a collision.
On the other side of this skin we have the ocean. One of the risks during a transport is a collision with another vessel. If the skin would be damaged, this whole tank could be filled with water.
But just like on the Chinese junk, bulkheads help the Vanguard to stay safe at sea.
In this vessel we have 96 ballast tanks, each of them surrounded by these bulkheads, running from starboard to port side and from fore to aft. Here you can see one of the bulkheads. These will prevent the water from flooding in the rest of the vessel once a tank would be damaged. This single tank could hold about 6,000 tons of water in itself. These steel plates and the enormous brackets will hold the pressure acting on the other side of this plate. Knowing that this tank is only one of the 96 ballast tanks, it shows the sheer size of this vessel.
The Vanguard is equipped with 10 bulkheads. 3 that run the length of the ship, and 7 across the width. Should the worst happen, these 20mm thick steel walls are capable of withstanding 50 tons of water pressure per square meter. They also provide structural support, helping the Vanguard bear the immense weights loaded on her deck.
These bulkheads are the backbone of this vessel. These are essential for the structural integrity of the vessel and the safety of the vessel in case of a collision. Without these, the vessel couldn't carry these huge cargoes.
Thanks to her world-beating achievements, the team responsible for engineering and operating the Vanguard are in awe of this mighty ship.
This vessel for me is the #1 heavy lift vessel transportation. It's the largest of its kind, has the largest deck space. So for me it's absolutely the #1.
What we do day to day is carry around cargoes that are extremely big, extremely heavy. And there are no other means of transporting them other than putting them on this vessel. It is quite impressive.
This ship is an amazing engineering achievement, and the engineer who designed this vessel are great.
At 275 meters long and 70 meters wide, the Vanguard is a vessel of truly vast proportions. Thanks to her truly immense ballasting system, arrangement of enormous bulkheads, innovative buoyancy casings, and pair of retractable rudder propellers, she's able to lift and transport loads that would otherwise be impossible. For all those involved with the Vanguard, being a part of this record-breaking project is a great source of pride.
In my opinion, this is a really incredible vessel, and there's no other vessel like this in the world. And for me, I'm very happy to be here and to be part of this.
By drawing inspiration from the pioneers of the past, supersizing their ideas, modernizing their technology, and facing down huge challenges.
The large cargoes we are moving are of such a size that this vessel, it's the only one in the world that can do it.
Engineers have built a truly awe-inspiring ship capable of feats no other vessel can achieve.
When you look out over it, it just boggles the mind to think about the amount of engineering that has gone into this and the sheer size of structures that can be brought on board and what we can do with them. It's just amazing.
They've succeeded in making the impossible possible. A remote outpost in Western Germany, home to NATO's main operating base. This specialist crew from around the world are constantly on alert. Their job? To spot hostile intrusion as they protect state borders that span the Northern Hemisphere.
The military are permanently on the lookout for different types of threats from all around the world. Hostile craft are in the air, on land, on sea, and they can come from all different directions. And without cutting-edge technology, protecting and defending is impossible. Hostile aircraft in particular are masters of camouflage because they can fly out of sight in valleys or behind mountains, and they can fly incredibly fast and low, all without being detected. The fundamental challenge for the military is to detect threats early so that they can react quickly and, if necessary, defend.
For over a century, engineers have been coming up with ingenious ways to improve military surveillance. During World War I, massive concrete structures were used to listen out for the enemy. But often it was too little, too late.
Oh dear.
Then along came radar, and by the 1930s they could see for miles. But only if nothing was in the way. More and taller towers were built to increase the area covered. But no matter how tall or how many were built, it was never enough. Modern-day engineers have now taken radar technology to the next level: the skies. This is AWACS. One of the planet's most sophisticated surveillance aircraft. Able to seek out, locate, and defend against threats, no matter how fast-moving or well hidden.
This is a massive and highly sophisticated machine. It's carrying 4.7 tons of ingenious technology on its back. 7.6 tons of equipment in the body of the plane. That's a staggering 12.3 tons of specialist equipment. And it's airborne.
The technology behind this amazing aircraft is kind of magic. It's just a tremendous piece of engineering.
This aircraft is like no other, able to see threats not only in the air, but also at sea. Operated by a specialist crew of engineers and technicians, surveillance experts and weapons controllers. Beneath the crew lie state-of-the-art signal amplifiers, the nerve center of this aircraft's most unique feature. An enormous 9-meter rotating radome, housing a 1 million watt radar system, with a scanning range of 300,000 square kilometers, an area larger than Arizona.
You are clear on engine number 2, target process. All right.
The AWACS technical supremacy also enables it to function as a flying command post for large and complex missions.
This incredible machine can be used to coordinate up to 150 aircraft at one time, and that's what makes it so extraordinary. There has never been an aircraft with this capability in military history. It's an impressively fast and accurate way of keeping the airspace safe. When the AWACS is in the air, nothing and nobody can hide.
Today, the crew have been scrambled to investigate suspicious activity due south. They'll be airborne for 12 hours.
Traffic 330.
AWACS is an incredibly complex piece of aviation equipment. The machine itself is awesome. The number of pieces that interplay is almost beyond comprehension.
And all the groundbreaking technology that's been added enables AWACS to carry out the most complicated of missions. But creating a machine like this poses massive challenges.
So how do you mount this huge radar system on the back of an aeroplane? How do you protect against a threat that's invisible? And once in the air, how do you stay there for as long as possible?
There's so many aspects of this aircraft that you would normally find spread over a huge area on the ground there. Nowadays, it is all in one plane. It's an incredible aircraft.
On the ground, engineers are working 24/7 on the AWACS fleet.
The aircraft is vital to the alliance here. We can do air battle management and various other activities. So the commanders regularly request AWACS support. It's an incredible aircraft.
But when you're flying over 800 kilometers per hour at 10,000 meters high, ensuring the radar system functions properly is full of challenges.
In order to put this vast radar system onto a plane, the first problem is the sheer size. All that power and equipment that would normally be in a large radar tower is now going on an aircraft. On the ground, you have plenty of space for your generator and cooling mechanism, but in the air, you simply don't.
As well as the size, the radome must be stable enough to withstand wind, vibration, and temperature, and the stresses of taking off and landing.
The radome also needs to allow the radio waves to pass through it, so there can be no internal structure that would compromise the signal.
For such complex engineering, inspiration was needed from pioneers of the past. The first long-range radar arrays were planted firmly on the ground. British radar systems throughout World War II were mounted on huge and heavy 110-meter towers. To come up with a solution to the problem of strength versus weight, engineers found inspiration in outer space. Kate Mulcahy is at London's Science Museum, looking at one of mankind's greatest achievements.
And here it is. This is the Apollo 10 command module.
Orbiting the moon 31 times. This is the actual command module from NASA's 1969 lunar program. This 3-crew mission to the moon and back was the dress rehearsal for the lunar landings that followed, and pushed engineering to the limits.
On its way back to Earth, the command module actually set the record for the fastest speed in a crewed vehicle at 39,897 kilometers an hour.
NASA's engineers had to build a spacecraft that could withstand the challenges of the 1 million kilometer lunar mission.
They had to build a module so that it was light enough to get to space in the first place, but it also had to be rigid and strong so that it could withstand the stresses of re-entry as well as deceleration forces of up to 6.7 G. And finally, it had to not buckle or collapse when it actually landed. And I can see part of the solution here. This is a honeycomb lattice that's sandwiched between two thin outer layers.
In 1638, Italian astronomer and scientist Galileo Galilei observed how honeycomb-type structures in bird bones increased strength without adding weight. The principles observed in nature inspired engineers to build their own honeycomb structures.
These sheets of paper clearly aren't very strong, but if I'm to take these same sheets of paper and instead use them to make tubes like this, if I then take the tubes of paper I've made and I attach them all together, I get a honeycomb type structure. Now, if I add a sheet top and bottom, what I'll end up with is a sandwich.
The exact same amount of paper that was once flexible is now rigid.
Now, the facings on this sandwich take the bearing load. That's the compression and the tension, and the honeycomb takes the shearing load. This structure is incredibly strong. Not only can it carry one brick, but actually it can carry much, much more than that.
Honeycomb sandwiches allowed NASA to meet the criteria of strength, rigidity, and low weight.
This can easily take 7 bricks. In fact, it could probably take more.
But engineers still faced the biggest challenge of all. On re-entry to Earth, temperatures would reach over 2,700 degrees centigrade, hot enough to melt most metals. The honeycomb was made of 370,000 individual cells. Epoxy resin was injected into each cell by hand. Engineers calculated the resin would melt in such a way that heat dissipated away from the inner structure.
Considering this was such a new technology, I can only imagine the thoughts of the crew as they were finally making their journey back to Earth.
3, 2, 1, left.
The ultimate test came as the module approached the Earth's atmosphere.
Hello, Houston, Apollo 10. We are returning to the Earth. Over. Glad to have you on the way back home, 10.
On the module's heat shield, the resin had burnt away, leaving layers of honeycomb and the inner structures perfectly intact.
It's amazing because this honeycomb sandwich not only saved the mission, but it also saved the lives of the crew inside.
Thanks to the honeycomb sandwich technology, 11 modules successfully made the hazardous journey through Earth's atmosphere and back to Earth over the course of NASA's lunar program. The NASA team had achieved the impossible. To create the AWACS radar system, engineers have taken honeycomb technology and combined it with state-of-the-art radar. The whole of the radome structure is formed from honeycomb, making it light enough to piggyback on a jet plane. Lieutenant Colonel Jens Meyer oversees the radome's maintenance.
I got some honeycomb material here. Let me just show you what this really is made of. Very flexible, very lightweight. This type of material, the honeycomb structure here, you can put an 85-kilo soldier on this and it will not move one bit. When you put layers of fiberglass on top of it, it also becomes very inflexible, so you have a very sturdy while lightweight structure that can withstand very strong forces.
The strength of these layers that form the radome means no internal bracing is needed. And the shape of the honeycomb allows radar signals to pass through the structure, uninterrupted and without distortion.
Without the honeycomb structure, it would have been impossible to manufacture the rotodome as it is today.
Okay, let's have a look at the antenna. So we are going close, forward.
Engineer Roger Snyder services the radar assembly.
Okay.
The radome's interior is the heart of AWACS. Only seen by the qualified few.
Up front, you see a motor who turns the antenna. The hydraulic motor makes it possible that the antenna is spinning at 6 rotations per minute. Up here, you have 3 receiver protectors and just below, low noise amplifiers.
But powering this million-watt system provides engineers with a further problem.
One challenge in transmitting at that high power, of course, is the heat that is generated by the transmitter. Therefore, we are cooling and stabilizing the temperature with fluoride carbonate, and therefore having a very stable temperature, what is important for the antenna to work as designed.
High temperatures inside could also cause the radome structure to distort, obstructing the radio waves. So the honeycomb's impregnated with a resin mix that helps maintain the radome's stability during temperature changes. It's the perfect environment for radar transmission.
We are able to work and pick up targets with less noise, therefore achieving a higher range.
Octane 58, Magic loud and clear.
Such a highly sophisticated cooling system is the only reason AWACS is able to achieve its mission.
33,000, passing from West East.
It's an extraordinary and seemingly impossible feat of engineering. With the honeycomb, cooling and radar equipment in place, AWACS can survey 360 degrees across an area of 300,000 square kilometers.
One of the challenges involved with monitoring large areas is staying in the air long enough to gather all the information that is needed. To maintain a tactical advantage, you must be able to gather enough data, and the longer the AWACS can stay at altitude, the better the air and sea pictures that it can provide.
AWACS can fly for up to 8 hours, but for some missions, pilot Micah Redfield may need to remain in the air for longer. The trouble is, the fuel consumption is dictated by the load he's carrying.
So we can take anything from 5,000 or 10,000 pounds to 100,000 pounds if there was a mission that really dictated that much on-load. So people in the past have been trying to solve the problem of air refueling in order to extend that mission duration and be able to provide better capability.
So how do you keep a 93-ton military aircraft airborne beyond its fuel capacity? For the answer, engineers look to one of history's greatest aeronautical inventions. Since we first flew, pilots have attempted to stay airborne for as long as possible. In 1920, a pilot tried to pick up a petrol can from a float. In 1921, a wing walker tried carrying a can of petrol from one plane to the next.
Imbecile!
And in 1923, pilots used a line to lower a petrol can to a plane below. All these attempts have been as dangerous and unreliable as they sound. In mid-30s Texas, Al and Fred Key were desperate to find a solution to achieve their goal, breaking the world record for the longest ever non-stop flight. They were flying a Curtiss Robin plane called Ole Miss.
Push the mixture in, throttle is set, area is clear, hit the starter.
Pilot Andrew Keast flies one of the few remaining Curtiss Robin planes.
Grab some fun. What's special about this airplane is it's a beautiful and graceful airplane as it flies. It's in its own class.
The Key brothers knew the Curtiss Robin would be the best plane to help them rewrite the history books.
The tubular design of the Curtiss Robin was a very strong design, so they were able to put a very large fuel tank in the back of the airplane for this endurance flight. And the structure of the fuselage was strong enough to support running boards on both sides of the airplane, and the pilot and mechanic would be able to go out and service the engine, change spark plugs, change oil, all during flight without having to shut it down and land.
The Key brothers had the perfect plane. Now they needed to work out how to refuel without stopping. The ingenious plan they came up with seemed simple enough. Spare fuel would be carried by a plane above, and a fuel hose would be lowered to the Curtiss Robin below. But mid-air refueling for real was to prove an almighty challenge.
I can't make it any better than that.
A fuel hose without a weight to steady it was lethal. Back on terra firma, Andrew's simulating in-flight conditions.
Here's an example of just a line with no stability device on it and how unstable it is. You can imagine what this would look like at 80 miles an hour.
Previous attempts had proved unsuccessful. Fred Key was hit in the face by a hose, and another pilot snared and dragged to his death as he struck the propeller. They had to figure out how to stop the fuel hose spinning dangerously out of control.
So the Key brothers looked into aerodynamics to find a way to stabilize the fuel hose, and one of the things they come up with was a basket they put on the end of the hose to stabilize it.
Andrew's going to test the cone-shaped device the brothers came up with.
Okay, here we go for a test. So coming through 10 miles an hour, it's lifting off the ground. There's 20 miles an hour. Well, it's flying and it's just holding in there nicely. It's just very stable. 20 miles an hour, it's working.
Equipped with cone-shaped aerodynamics, at last the fuel hose could be managed safely at altitude and at speed. On June 4th, 1935, the Key brothers set off on their record-breaking attempt. With mid-air refueling mastered, the Key brothers were able to receive more than 6,000 gallons of gasoline. The brothers achieved an astonishing world record. They flew their Curtiss Robin non-stop for 653 hours and 34 minutes. 27 days in the air.
Key brothers were definitely aviators of the day. They truly were test pilots. They helped engineer aerial refueling. It's a major thanks to engineers and early aviators that really paved the way to what we have today.
Modern mid-air refueling rigs use aerodynamic designs pioneered by the Key brothers.
And you're established.
Copy.
The probe and drogue system is the industry standard.
As technology has progressed, that has developed into the probe and drogue system. So having essentially a parachute at the end would stabilize the movement of the hose system, and the drogue became a much more effective tool.
Chain 42 is disconnected. And he's off to the right.
Despite the proven technology of the probe and drogue system, refueling AWACS is a much bigger challenge for pilot Micah Redfield.
A heavy aircraft like the AWACS is not as maneuverable as a smaller fighter might be, because the AWACS just simply isn't capable of maneuvering quickly enough to use a drogue-style traditional system.
We won't be able to see him, but he's coming back soon. Copy that.
Engineers had to take the refueling system to the next level, a remote-controlled flying boom. Approaching the tanker plane, Micah must use the utmost skill.
The pilots will proceed visually up to get within 50 feet of the tanker initially.
Maybe to the left?
Yep.
Perfect.
At that point, the pilot will stabilize the aircraft and try to neutralize any aerodynamic forces that are affecting the aircraft.
40 feet.
30. 20 feet. 10 feet.
Flying on full manual control at 500 kilometers per hour, just meters below a tanker filled with fuel, is one of the riskiest maneuvers Micah will ever have to face.
It does become quite complicated, and it's a very physically demanding skill for pilots to develop. It is something that takes a lot of concentration and effort.
Clear for contact. Off to the right.
The boom operator is sitting in the back of the tanker aircraft, and they have a joystick that can actually fly winglets on the boom to move into position.
Six one contact. I'm pumping. Copy.
With an incredible 3,700 litres of fuel being pumped into the AWACS per minute, the crew are all on high alert.
The system has always been an inherently dangerous problem. There's a bit of nerves every time you go up, but you still have to be very conscious of what you're doing and what you need to do to execute safely.
Having safely docked and received thousands of litres of fuel in mid-air, AWACS is ready to go.
The people who pioneered air refueling were incredible aviators and also just incredible human beings. They were figuring it out all for the very first time. It was really amazing what they were able to do, real pioneers of aviation.
On top of the plane, the 9-metre rotordome houses a 1 million watt radar assembly. The radar ancillaries and cooling systems extend through the fuselage and wings. Inside, 3 technicians, 5 surveillance crew, and a tactical director manage the data. The radar system enables AWACS to see an area of 300,000 square kilometers below.
The radar is delivering a lot of raw data that's being processed onto the screens for the individual to actually assess whether an aircraft is a friendly, is a foe, whether it's a fighter aircraft, whether it's just a transport aircraft. They provide a consolidated air picture for the commanders on the ground.
But it's the invisible threat that causes the most destruction.
One of the major challenges when designing the AWACS is how to keep the aircraft flying during a nuclear war. In the event of a nuclear explosion, electromagnetic pulses are released that can disable some of the sensitive equipment on board, rendering it completely useless.
So how do you keep AWACS safe from an invisible enemy? To find out, engineers had to look back at the biggest bomb blast of its time. In July 1962, the US carried out the Starfish Prime nuclear test.
Starfish Prime was launched and was entirely successful.
Exploding a 1.4 megaton bomb 400 kilometers above the Pacific Ocean.
A tremendous amount of data was recorded during these events.
The blast caused a sudden and rapid acceleration of charged particles, called an electromagnetic pulse, or EMP. Similar to a bolt of lightning, the pulse was so powerful it destroyed electrical components over 1,000 kilometers away.
We do need more information on this fireball blackout.
With the threat of nuclear war still around today, AWACS must be protected from the destructive effects of EMP.
Okay, sign says off limits to non-essential personnel, but I've got permission, so let's take it through the gate and see what's behind it.
Dan Dickerell is visiting a top-secret US Air Force facility to find out more.
It doesn't look like anyone's been here for years. Weeds are growing up through the road. What an amazing place. So this place is really off limits. No one gets to come here. I've heard about it, and oh, there it is. That thing is huge. That is something else.
In the 1970s, engineer Dr. Carl Baum built an EMP test facility at Kirtland Air Force Base in Albuquerque, New Mexico.
All right. Let's go have a look.
Decommissioned and out of bounds since the early 90s, the site is still a masterpiece of engineering.
Oh, wow. This massive structure is 1,000 feet long and 125 feet high, and it's the world's largest structure made entirely of wood and glue. It's called the Atlas Trestle.
Built at a cost of $60 million and constructed with 6.5 million board feet of lumber, the trestle was strong enough to support a fully loaded B-52, then the largest and heaviest bomber in the US inventory.
Aircraft would taxi down 1,000 feet to the end of the trestle, perched above the ground as if it were in flight. Once we were in position, two massive generators on either side would unleash a 200 gigawatt pulse in less than a millionth of a second. That energy would be directed down these transmission wires. This pulse would simulate the EMP generated by a nuclear explosion.
The engineers knew how to generate EMP, but the bigger challenge was simulating its effects in flight.
Now, the ground can affect the EMP readings, but also the trestle itself, the structure. So the solution to this was to create the entire thing out of wood, no metal at all. These giant, large timbers, even the nuts and bolts are made of wood, and I have an example of one here. The wood is impregnated with a phenolic resin. It makes it very strong, but also EMP transparent. The combination of all of these solutions meant the EMP results would not be affected.
With the trestle itself shielded from interference and the EMP generators working at the optimum configuration, engineers could apply stress to specific aircraft components and so determine how to best protect flying planes from nuclear attack.
So the solution looks something like this. Here I've got two phones. I'm going to call this phone from this phone. As I dial my number, what we'll see is the radio waves go from this phone to the mobile tower, transmitted through the atmosphere. And here we see the phone call is being made. So it works. What I can do now is I can trick this phone into not receiving the call. So I'm going to take this phone and I'm going to wrap it in this fine wire meshing. This phone is now safely encased. Okay, so let's try this again. I've got my phones. When I make the call this time, I'm going to listen. The call is being made. The radio waves are going through the atmosphere, but the receiving phone is not ringing.
The trestle engineers were using a principle first devised in the 1830s.
So we had constructed a Faraday cage. How does that work? Well, in the atmosphere, we have electromagnetic waves that are traveling through, in our case, radio waves for the cell phone transmission. If those waves encounter a barrier where the holes in that barrier are quite small, smaller than the wave itself, the wave cannot penetrate that barrier and is forced to go around. So the wave can't pass through the barrier because the hole is too small. And this principle is the same principle that is used to protect aircraft from the harmful effects of atmospheric EMP. By testing certain planes and seeing how the energy dispersed across its wings and fuselage, the data gathered could be applied to other planes' designs as they evolved.
Many plane designs benefited from EMP testing, making the Atlas trestle one of the great secret engineering feats of the 20th century. Engineers have applied everything learnt from the past to create AWACS.
They actually designed this aircraft being a big flying Faraday's cage here. So the fuselage made out of metal there, that will route all the energy around the precious electronics in the inside.
AWACS is engineered to be the most EMP-resistant plane possible. An aircraft structure designed and built to withstand and redistribute electrical charges. Door seals fitted with EMP-conducting gaskets. But the EMP proofing doesn't stop there.
All the cabinets inside the aircraft are also smaller Faraday's cages here, protecting all the electronics inside even further.
And the sensitive radar equipment is shielded too.
There are also filters in the lines from the antennas, filtering out whatever spikes of electromagnetic energy is coming through there.
But there's still one more challenge: the plane's windows. Glass doesn't stop EMP, so the windows are laced with a fine wire mesh. The holes are smaller than the electromagnetic waves, so they won't pass through it. And the crew can see out.
Left, you can do 180 left, easy, inbound CP. Okay.
100. The runways is set.
Yep.
50. 40. 30.
The mission today has analysed a huge amount of data to build a clear picture of activity across the Mediterranean, in and out of North Africa. The classified information has been relayed directly to Allied NATO forces.
Excellent, Data 11.
No wonder AWACS has been declared the most significant single tactical improvement since the advent of radar.
It's incredible how people manage to overcome all these challenges, putting radars in here, electronic systems here, inertial navigation systems. This aircraft is just a tremendous piece of engineering, and I'm actually very glad that I'm allowed to help maintaining it.
AWACS is the jewel in NATO's crown. It is a triumph of the skies and has pushed the boundaries of what man thought possible. It's one of the most impressive radar aircraft ever built. Capable of staying in the air even during a nuclear attack, the AWACS can detect threats and pass on vital data and information to military units on the land, sea and air. Just the fact that a 9-meter diameter rotating radar housing a 1 megawatt radar system can take to the skies is an incredible feat of aeronautical engineering.
A highly modified aircraft, 46 meters long with a wingspan of 44 meters, able to refuel in mid-air. 7.6 tons of equipment in the body of this reinforced machine, capable of withstanding the effects of a nuclear war, and mounted on top a 9-meter diameter rotating radar assembly housing a 1 million watt radar system. AWACS has pushed the boundaries of engineering.
I have to say I love this system. It's one of those aircraft you really have to love as an engineer, because there are so many challenges that had to be overcome by ingenious engineers here, and for me it's an incredible aircraft.
By drawing on the innovators of the past, adapting, upscaling, and conquering many challenges, engineers have created a plane like no other.
Those moments that you can stop and step back as you walk out to an airplane and you see it, you really appreciate how much has gone into aviation, and you get a little of the joy of why you started flying in the first place. So I enjoy it. It's a great experience.
And its success will be far-reaching.
It has taken decades of innovation. This is a triumph of engineering that has to be seen to be believed.
The AWACS engineers have succeeded in making the impossible possible. The United States military, home to the largest fleet of fighter aircraft on the planet. They're the essential tool of modern warfare.
Carry strike group 10.
Capable of defending airspace over land and at sea, anywhere on the face of the Earth. But with the potential for conflict to arise at any moment, staying one step ahead of an unknown enemy with unknown capabilities presents an enormous challenge. At Naval Air Station Lemoore in California, master jet base of the Pacific Fleet.
Level 13, Lemoore ground, taxi to line, Dear Bravo.
Commodore Max McCoy is part of the team responsible for ensuring that the US can maintain dominance of the skies.
Controlling airspace is absolutely critical. It gives us the flexibility to control the contested battle space. It gives freedom of navigation to respond anywhere in the world to an emerging crisis.
But ensuring that war in the air remains a one-sided fight is a relentless engineering battle, where technology can mean the difference between life and death.
The United States needs to continue to develop new aircraft because there is emerging threats worldwide, and we have to outpace that threat and ensure that we stay ahead so that we can continue to dominate the battle space both on the surface and in the air.
Ever since man first took to the skies, engineers have been trying to assert their military might. In the 1700s, French chemist Jean Coutel built the world's first military balloon to spy on enemy movements. Next came the colossal airships designed by Count Ferdinand von Zeppelin. They could carry bombs over long distances, but one stray spark and you were in trouble. By the time of the First World War, the airplane had arrived, revolutionizing aerial warfare. But in the early days, things were pretty basic. Pilots would use rifles, grenades, or even grappling hooks to take down their enemy. Today, engineers have pushed the boundaries of aviation technology further than ever before and created a brand new, revolutionary fighter aircraft. The F-35 Lightning II. This multi-role fighter is the most technologically advanced aircraft in the world. Capable of handling threats in the air and on the ground. It will also be operated by 9 partner nation militaries, including the RAF in the UK, Italian Air Force, and Royal Danish Air Force.
The F-35 is the most advanced weapon system in the world. It is a catalyst for changing how we maintain, sustain, and fight aircraft, and it will definitely be a game changer.
For me, flying the F-35 is amazing. The aircraft's combination of maneuverability, speed, altitude, endurance.
Designed in 3 variants, the F-35A for the Air Force, B for the Marines, and C for the Navy. Each can reach a top speed of 1,900 kilometers per hour, over 600 kilometers per hour faster than the speed of sound. This immense power is produced by an engine capable of generating more than 40,000 pounds of thrust, making the F-35 a staggering 10 times more powerful than the first jet fighters, delivering a gigantic 9,900 kilograms of weaponry anywhere on the planet.
The F-35 is the most capable, survivable, lethal, adaptable, and flexible airplane in the world today.
But this ambitious project presents some formidable engineering challenges. How do you design and build a single aircraft for 3 distinctly different branches of the military?
Building an aircraft that not only is a multi-role fighter, but has the reconnaissance capability, the advanced sensors that the F-35 has, is a challenge.
How do you make an aircraft traveling at almost 2,000 kilometers per hour disappear?
As a pilot, it's virtually impossible to comprehend the level of detail and advanced engineering required to make something roughly 50 feet by 40 feet, virtually undetectable or invisible to radar.
And make a 20-ton airplane defy the laws of physics.
When we set out with the engineering challenge of being able to take 40,000 pounds of airplane and land it vertically, almost seemed insurmountable.
The United States military has a new way of defending its airspace. The cutting-edge F-35 Lightning II. Built to travel at 1.6 times the speed of sound, and capable of withstanding 9 times the force of gravity. It can strike anywhere on the planet. But building the world's most advanced war machine is a daunting challenge for Santi Bulnes, Vice President of Engineering for F-35 manufacturer Lockheed Martin.
Every service, whether it's Air Force, Navy, or Marine, really counts on its aircraft to go do what it needs to do. And it is important. Why? Because it is the first thing that you go into war with.
But after decades of each service using different aircraft, an ambitious plan is formed. One airplane, built in 3 variants, will be used by the Navy, Marines, and Air Force.
There have been several attempts in history to build a one-size-fits-all fighter for folks, and it's ended up being a little bit disappointing.
Santi and the team of engineers must learn from the mistakes of the past.
The military wanted a new aircraft to be able to do multiple things. It couldn't just be a one-trick pony. It needed to be able to fly far to go where it needed to. It needed to be able to go supersonic to achieve the speeds needed to be an effective fighter. It needed to be stealth so that it could penetrate enemy defenses. Pulling all that together to be a next-generation multi-role fighter, one aircraft that meets the needs of all the services is quite a challenge.
To create the perfect plane, the team must look at how it was done by the pioneers that came before them. High above the Florida coastline,
What a fantastic airplane.
pilot Rob Collins is putting a game-changing piece of aviation engineering through its paces.
I can't help myself. We're going to do that again. Look at that thing go around. Wow! Back in 1937, the U.S. Army Air Corps sent out a request for a new type of multi-role fighter.
This new aircraft would need to be capable of taking off from a short runway, climbing to 6,000 meters in 6 minutes and having a top speed of 640 kilometers per hour.
This was a rather radical request at the time, and the engineers would really have to think outside of the box to develop a new design and engineering solutions that never before were possible.
Engineer Clarence Kelly Johnson and his team at the Lockheed Martin Corporation started development on a top-secret prototype, a project that would revolutionize the multi-role fighter aircraft.
This is the Lockheed P-38 Lightning, one of the most unique fighter planes of World War II, and I personally think the most beautiful. There's no fighter plane that has such a look. The twin booms, this gondola in the center, it is absolutely stunning.
Considered the first true modern multi-role fighter aircraft, the P-38 was capable of attacking targets in the air, on the ground, as well as carrying out vital photographic reconnaissance missions.
Back in the 1930s, we have to remember aircraft at that time were mostly open cockpit biplanes. To be the interceptor that the Army Air Corps wanted was a tall challenge.
To solve the speed challenge laid out by the Air Corps, engineers devised a simple solution.
Kelly Johnson came up with a very unique way of solving this issue. They made it twin engine, not a single engine fighter.
With no single engine capable of producing enough power to get the P-38 to 640 kilometers per hour, he added a second, doubling the amount of thrust.
The engines in the P-38 were an Allison 1710. They're a V12 liquid-cooled engine. In the L model, this aircraft here, they produce 1,600 horsepower each.
These two engines, combined with the aircraft's smooth, aluminium flush-riveted design, pushed the P-38 to speeds of more than 640 kilometers per hour. 160 kilometers per hour faster than other fighters of the day, and way over the Air Corps' requirements.
Making an engine that could fly high enough where it could be a successful interceptor at altitude, that was an amazing accomplishment back at that time.
But to be a success, the P-38 also had to meet the Air Corps' other requirement. To demonstrate this capability, Rob is once again taking to the skies.
Houston to ground. Lightning 505 Mike Hotel, American Aero, ready to taxi. 11.
Lucky 505 Mike Hotel, roger, taxi via Delta.
The Air Corps demanded their new fighter be capable of getting airborne using just over 600 meters of runway. So, is the P-38 up to the challenge?
45 inches, you can hear the turbos start to wheel. The whistling of the turbos are really pronounced in this airplane. There's about 1,000 feet, and we're off the ground. this airplane flying. Look at that, 2,000, 3,000 foot of rate of climb.
With a maximum climb rate of over 900 meters per minute, the Air Corps' final requirement had been met. The P-38 was one of the most successful aircraft of the Second World War, achieving engineering feats beyond the reach of what was considered possible at the time.
It's an incredible aircraft to fly. It's so maneuverable, fast and responsive, and it really laid the foundation for modern fighter planes today.
Today, engineers have taken the lessons learned by their predecessors on the P-38 and inserted them into the DNA of the F-35.
This is the F-35C Lightning II. It's the U.S. Navy and U.S. Marine Corps' carrier-capable version of the Joint Strike Fighter designed to launch from and recover to Ford and Nimitz-class aircraft carriers.
Commander Mark Cochran is part of a small group of pilots trusted to fly the Navy's brand new, over $100 million weapon.
The F-35 Lightning II takes its name from the P-38 Lightning, made by Lockheed Martin Corporation during World War II. Both aircraft were cutting edge for their day, both aircraft were multi-role, and both aircraft are going to be used across all theaters of conflict.
But despite their similarities, the F-35 has capabilities engineers in the 1930s could have only dreamed of.
All right, so from front to back, some sensors that you'll find on the F-35 are some mission systems. At the front, you're going to have an active electronically scanned array radar. They can locate targets just by their physical presence. After that, you're going to have the electro-optical targeting system. It's going to allow us to target aircraft and ground targets via their IR signature. Above that, you'll have the distributed aperture system, or DAS, which its primary function is missile warning, so to see missiles launched by another aircraft. However, it also provides the pilot the ability to see in the dark. Moving aft, we're going to have the largest wing of the F-35 family, and that's designed for increased maneuverability. It increases our range.
Arguably the world's most cutting-edge weapon of war. Just like its predecessor, the F-35 still requires a human at the controls.
Sitting on the flight line or on the flight deck in an F-35, waiting to take off is one of anxious excitement.
Once airborne, Mark will be at the controls of a supercomputer, capable of completing more than 400 billion operations a second, whilst traveling at speeds up to 1,900 kilometers per hour.
Having a massive jet engine whining behind you and getting ready to engage the motor, accelerate forward is surreal at times.
Mike Hotel, give the tower call when you're ready.
In the air, the F-35 is unrivaled. Its massive single engine puts out over 40,000 pounds of thrust, making it the most powerful fighter jet engine on the planet.
Airborne visibility is excellent, maneuverability is excellent, payload, range, altitude, airspeed are all better than our legacy fighters that we fly in the Navy. The F-35 is the smartest and most deadly aircraft in production.
But where do you start when faced with the challenge of constructing the world's most advanced fighter jet? At the F-35 factory in Texas, the task of turning raw materials into a fully fledged war machine is the responsibility of senior fellow Don Kinnard.
There's about 7.5 million square feet total here in Fort Worth for building the airplanes plus storage.
1.5 kilometers long and covering an area the size of over 130 football pitches, the F-35 factory is one of the most advanced in the world.
Well, first of all, we get lots of parts. So for the wings and forward fuselages, we get composite parts, metal parts, tubes and wires from all of our suppliers.
Each station on the factory floor carries out a specific role. At one end of the mile, the forward fuselage, nose and cockpit section is assembled, whilst at the other, the wing sections are formed and mounted together. At final assembly, the control surfaces are added and the F-35 gets its Pratt & Whitney engine, before leaving the factory for final checks and flight testing.
This aircraft is about as advanced as it gets in terms of technology.
But making an aircraft this advanced requires more than just a well-oiled production line.
So in the old days, we used to take the drawings and a mechanic would put out the drawing. These are 20, 30-page drawings, and he would start writing down on every fastener with a marker what fastener went in what hole, and then we'd get that panel on the airplane, and then they'd have to put it up, and then he'd follow that to put them in.
Today, through the use of optical projection, Don and his team are revolutionizing aircraft manufacturing.
What we're doing is I'm lighting up the fasteners on this big cover on the airplane. So for example, here, I'm saying I want to put this particular fastener in these particular holes. You get a lot better quality, making sure the right fastener goes in the right hole. We now have about 200 of these systems all over the factory that do projections like this. So this has been a real big success for us.
Thanks to systems like this, after more than 18 months of work, a completed F-35 rolls off the line, ready for deployment.
What comes in is a bunch of parts, pieces, and components from all over the world. What leaves here is a completed F-35.
The F-35 Lightning II is the most technologically superior fighter jet ever built. Over 8 million lines of code ensure its onboard supercomputer keeps the pilot one step ahead of the fight. Back in Fort Worth, Texas, a revolution in aviation engineering is occurring, as they build the most technologically advanced fighter jet on the planet. The F-35 Lightning II, made from over 250,000 individual parts. It takes over 18 months to turn the raw components into a state-of-the-art fighting machine. But before the F-35B variant can get in the air, engineers face another challenge.
The Marines wanted an aircraft that would land on their smaller carriers, not as large as what the Navy has, so those carriers require an aircraft that will land vertically as the Harriers do today.
First entering service with the Marine Corps almost half a century ago, the Harrier has been the aircraft of choice thanks to its almost unique ability, the vertical landing.
So the Marines wanted this plane to have maximum flexibility for them to be able to fight their wars.
73 Regional 79 Auto.
But hovering an airplane that's over twice the weight of the Harrier challenges every rule of aeronautical engineering.
The F-35 is about a 40,000-pound aircraft, and getting that much weight to hover, and to hover in a stable fashion, is an engineering challenge.
So could the solution lie in the innovations of the past? At a secret location in the USA, test pilot Andy Edgell is uncovering a unique aircraft that transformed aviation engineering on Earth and in space.
Very excited. This is one-of-a-kind aircraft. This is phenomenal, absolutely phenomenal. This is the Bell X-14. This is the only one in the world. This is the only X-14 that was ever built. What a fantastic machine.
Built under top secret conditions, the X-14's mission was to see whether it was possible for a jet airplane to take off and land vertically.
The big challenge is here you've got a 4,000-pound aircraft. on Earth. Gravity takes effect, tries to pull it down to the ground. If you want to just take the aircraft off vertically, all of the thrust that you need to achieve needs to go straight up, and it needs to be bigger than the weight of the aircraft.
Designed by engineers at the Bell Aircraft Corporation in New York, the X-14 prototype was constructed mainly from existing parts in just 3 months.
All right, let's pull this out and have a good look at her.
To understand the engineering behind this one-of-a-kind airplane requires Andy to maneuver it out of the hangar for the first time in decades.
Pretty phenomenal moment to pull this one out. These two engines, they're tucked neatly into the fuselage. They're not out on one wingtip and the other wingtip. And the reason for that is you want everything all nice and close and in line with the center of the aircraft. Because eventually what we're going to try and do is balance this aircraft on a column of air.
Each engine produces over 3,000 pounds of thrust, enough power for a conventional takeoff. However, the key to vertical lift and landing isn't producing thrust, it's in directing it precisely.
This is where the magic happens. This is the crown jewels of the X-14. The air that comes out of the engine, that exhaust, gets pushed out in a direction that is decided by the pilot. So the pilot can choose which way he rotates these nozzles and directs these vanes. In doing that, what he's essentially deciding is where to propel the air out of the back of the engine. If he positions the nozzles to go straight down, the aircraft will go up. And there, when it's coming straight down, the aircraft is just balancing on a column of air. What we see here is the first ever thrust vectoring aircraft.
The team at Bell had solved one of the greatest challenges in aviation engineering. But it was only half the battle. They must also come up with a control system that lets the pilot maneuver the airplane when in the hover.
Now, in conventional flight, when you're going forwards through the air and the air is blowing over the wing, we control it by moving these surfaces. They're called the ailerons. If the pilot wants to move left, he moves the stick to the left aileron goes up, the right aileron goes down, and that means more lift is produced on the right wing than the left, and the aircraft rolls left. Very simple. So the situation we're looking at right now is exactly the same as the situation when the X-14 is sat in the hover. The pilot can move the stick all he likes, and the ailerons will move all they like, but the aircraft's not rolling.
The system works by taking excess air from the engines and directing it to nozzles located on the wingtips and rear fuselage. As the pilot moves the stick, the nozzles either open or close, releasing high-pressure blasts of air, directing the aircraft in roll, pitch, or yaw.
So when I move the stick to the left, the duct closes, there's no jet of air that comes out, there's a big puff of air that comes out on the other side, and the aircraft rolls.
In the late 1950s, the X-14 rewrote the aeronautical engineering rulebook, becoming the first American jet aircraft to achieve the vertical takeoff, transition to conventional flight, and vertical landing.
Now this is incredibly exciting for me. I can officially say that I have sat in an X-plane. I can immediately identify that here is the nudging of the nozzles, and it even says horiz for horizontal and vert for vertical. So if I were to pull back on this switch here, it's going to rotate my nozzles down and sit me nice and stable on top of that column of air.
After proving the concept of vertical takeoff and landing was possible, in 1959, the X-14 was transferred to NASA, where it helped train Apollo astronauts to overcome the biggest engineering challenge in history, landing on the moon.
The fact that Neil Armstrong was sat in this seat flying this aircraft. This is a once-in-a-lifetime opportunity that I just never thought that I would get. For its time, the X-14 was groundbreaking. There was nothing like it in the world. Everything after it evolved from this. They proved the concept in the X-14. They made it better in the Harrier. They improved it further in the F-35, but it all started here in the X-14.
For the F-35B, engineers have taken the raw elements of the X-14 and improved them for modern warfare. At the F-35 factory in Texas, Chief Test Pilot Alan Norman is getting hands-on with this upgraded thrust vectoring system.
Every time I get in the airplane, I know it might sound cliche, but I almost have to pinch myself a little bit for how much fun I'm going to have. One of the easiest things about the airplane is, honestly, one of the hardest things about other airplanes, which is to get this airplane in the configuration to hover and the ability of this airplane to hover. For the pilot, all it is for us is a few button switches.
The centerpiece of the F-35B's thrust vectoring capability is its Rolls-Royce lift fan. As the pilot engages hover mode, it reveals itself and begins rotating, reaching 29,000 horsepower, drawing in enough air to empty a squash court in just over 1 second. Connected to the main engine via a drive shaft, it produces a downward flowing column of air at the front of the plane. At the rear, the exhaust nozzle twists, aiming its thrust toward the ground. For directional control, bypass thrust from the main engine is directed to outlets located under the wings, allowing the F-35B to gently touch down. But how difficult is it to land an aircraft weighing almost 20 tons vertically on a carrier in the middle of the ocean?
Well, we have a ship out in front of us. We're in the transition to a hover mode. The engine's twisted around, the lift fan is engaged, and then we're coming abeam the ship at sea. We'll pull next to it and then try to land aboard it. So we'll come down in altitude, and you can see off to my right is the ship. And now that I've picked out where I'd like to come down, I'll come right down on the deck. Piece of cake.
The F-35B's lift fan system is genuinely unique in the world of aviation.
My first impressions when I saw the very first F-35 were what is going on. To see 20 tons floating in the air, rock solid, not moving. I thought it was fantastic.
This technology will ensure the F-35B rules the skies for the decades ahead. In service since the mid-90s, the Super Hornet is now lacking an important feature essential to modern warfare.
Even though they're advanced, they still have a problem where they are visible to radar and they can't penetrate integrated air defense systems as far or as effectively as a newer, more modern aircraft.
As anti-air defenses have developed and improved, this visibility to radar can mean the difference between life and death.
If I were mounting a radar console looking for an F-18 Super Hornet, without any other support, it'd be easy to pick it up.
But could the solution to making an airplane invisible to radar already exist? To find out, engineers must look to the innovations of the past. At the National Museum of the United States Air Force, retired pilot Mace Carpenter is uncovering the engineering secrets behind one of the most classified aircraft ever built.
Wow, this is incredible. I never thought I'd be an F-117 again. The last time I sat in an F-117 was the year 2000. You know, it's kind of funny, and it may be ego, but I think I could get it in the aircraft today and fly it without a problem.
Conceived in the midst of the Cold War, the F-117 was designed to slip undetected into enemy territory.
Radar has been a nemesis of strike aircraft since World War II. The bulk of enemy air defense systems use radar for acquisition and for target tracking, guiding their missiles into the aircraft. So the goal was to reduce the enemy's ability to be able to see the aircraft until it was too late.
At the top-secret Lockheed Martin Skunk Works in California, engineer Ben Rich and his team started plans for the world's first stealth strike aircraft. The problem they faced was finding a way to overcome decades of radar research and development.
This is kind of a rudimentary demonstration on how radar might work. The flashlight will be my radar transmitter, and the mirror is a conventional aircraft. If I shine my light directly on the conventional aircraft, the light comes back to me as a very bright beam, a very bright return. Now, if this beam that was returning to me was radar, I would be able to pick up the aircraft from a very long distance. This is what's happening with most aircraft in the world. They're easily tracked by radar, but when you're a strike aircraft trying to penetrate defended airspace, it's bad.
So instead of the smooth aerodynamic lines found on other aircraft, engineers started testing a faceted, angular-shaped airframe.
Now I have a different mirror, and again, the light is the radar. The mirror represents the F-117. When I shine a light on this mirror, the vast majority of the light is reflected away and not back at me. And this is how the F-117 works. The radar is largely reflected away.
By reflecting radar energy away from the aircraft, engineers were able to drastically shrink the radar signature. But the F-117 would require further engineering to become a ghost of the sky.
The most important feature of the F-117 that makes it stealthy is the shape. 85% of the stealth. The other 15% is accomplished by putting radar-absorbing material, or RAM, onto it.
The exact makeup of this radar-absorbent material is still top secret, but it's believed to be made from thin sheets of a composite material, coated in iron ferrite paint that contains microscopic spheres. When hit by radar energy, these spheres vibrate, turning the energy to heat, which is absorbed by the plane, further reducing the reflection.
Hopefully we were a ghost and not seen. If we were seen, we weren't seen for any more than we had to be, or not enough time for the people on the ground to react.
The introduction of stealth technology changed the way war is waged from the air.
When the F-117 was designed in the mid-70s, it was at the pinnacle of aviation design. There was nothing that could touch it for decades.
Engineers working on the F-35 have taken ideas behind the F-117 and enhanced them for modern warfare.
Where the F-117 was an early introduction to stealth technology, radar resort material, the F-35 is the third step, or the third generation of that evolution.
Modern supercomputers have allowed engineers to calculate radar returns from curved surfaces, something not possible in the 1970s, giving the F-35 a vast aerodynamic advantage over its predecessor.
Lucky 505 Mike Hotel, roger, taxi via Delta.
However, despite the gigantic leap in technology, one thing remains the same.
The low observable technology that's resident in the F-35 is highly classified. You have to have a validated need to know and be part of the program in order to access it.
What can be revealed is that just like the F-117, the shaping of the F-35 provides most of its stealth capability.
If you look at the aircraft top down, you see that the front edge, the forward edge of the wing is going to match the front edge of the horizontal tail, which is the aft control surface.
Known as planform alignment, this improved stealth design orients key flight surfaces at the same angle. The result, radar energy is scattered away from the receiver in a precise direction, rather than diffusing it where it could still potentially be detected.
Low observable technology isn't something that has an on-off switch. It's something that has to be built into an aircraft from the ground up.
The combination of all this engineering makes the F-35 a ghost of the sky.
What it provides to you is it gives you more space to operate in. So because I don't have to worry about a threat seeing me as far away, that's white space in which I can move in and operate on my own terms.
For the team behind this incredible airplane, the sense of achievement is untold.
When I think about all the engineering and all the technology that's gone into the F-35, I'm still amazed to this day. Everything that we've done, everything we've put into it, and honestly what will carry on way past the F-35's day, that changed how we fly, what we do.
When I see an F-35 flying, and I don't care what variant it is, I feel absolutely proud. I've worked on this program in many different aspects over the years, and it just knocks my socks off every time.
This extraordinary airplane has redefined aeronautical engineering. 1.6 times faster than the speed of sound, practically undetectable to radar, and capable of a pinpoint landing. It's achieved unprecedented feats. The perfect mix of power, maneuverability, and precision. It's a feat of engineering few thought possible.
F-35 is the most incredible aircraft ever constructed. You look at how well it flies, when you look at how well it does its mission, this aircraft's going to be enduring for this country and its partners for decades, and I'm very proud of that.
By looking to great pioneers of the past for inspiration, adapting their ideas, refining their designs, and overcoming monumental challenges.
Every time I fly one of these airplanes here at the factory, I'm so proud. I see them flying in the air at a base, and I feel like a proud papa when I look up in the sky and see my kids up there flying. It's tremendous.
Engineers have built an age-defining airplane and succeeded in making the impossible possible.
I was a child of the Apollo era. You know, I stayed up late one night to watch them land on the moon. I was taken by that, and probably that influenced my whole life. Just being able to see something like that, you knew it was a miracle that we were there, a technological miracle. And the F-35 is that kind of program.
Guizhou Valley in China. 565 meters deep, it's known as the crack in the earth. This immense chasm has separated the local community for centuries. New York-based architect Wendy Fogg has traveled to this remote region to see how extraordinary engineering is pushing the boundaries of what's possible.
Canyons are pretty dramatic. It's beautiful around here.
She's attempting the hazardous journey to cross the valley.
It's kind of crazy ride. Roads are really bumpy, and the only way to get from one side of the county to the other is through this road. It's very frustrating because it's a 5-hour drive.
The long trip down the steep slope and up the other side is perilous.
It's dangerous, the road, because there's a lot of sharp rocks, lots of steep gorges. You also see a few landslides, so piles of rocks on the side of the road, so drivers have to be very careful.
This divide has a devastating effect on the community.
There's 35.8 million people in this region of Guizhou. With all these windy roads and steep valleys, it's very difficult for the local farmers to get the goods out of this county to sell them. So as you can imagine, it is one of the poorest regions in China.
A solution is desperately needed. But with over half a kilometre drop to the valley floor, nobody has ever bridged a gorge this deep. Crossing canyons has always been tricky. In the 2nd century BC, a Himalayan silk trade road used 100 hairpins to zigzag down a canyon. But today, that makes for a treacherous drive. In 1936, inspired by banana hoists, engineer James Curran came up with the first chairlift. Great for skiers, but not if you have a car. And in 1974, Evel Knievel tried to cross the Snake River Canyon with a rocket. But that didn't go to plan. Oh, darn! The solution engineers in China have come up with is breathtaking. This is the Beipanjiang First Bridge. With a deck 565 meters above ground, it's the highest bridge in the world.
It is super dramatic to be under this bridge. It's beautiful, and it is remarkable how high this bridge is and how long it extends.
At 1.3 kilometers long, it's one of the longest cable-stayed bridges on the planet.
It seems impossible to build a bridge here. It's very challenging.
Liu Bo is Deputy Chief Engineer of the bridge.
So this is the Beipanjiang Bridge.
Yeah. Normally off limits to pedestrians, he's giving 2 colleagues a unique tour.
It's very high. Very high? Yeah. When we came here, it's very difficult to go to the 2 sides. Yeah. What's your feelings? Huh?
It's really amazing.
Amazing bridge.
This is the first time I come here. For today, I only see this bridge on computer, but we'll see this real thing. It's really amazing.
It's the highest bridge in the world now. Yeah.
Such a beautiful bridge.
The bridge is made up of a pair of massive concrete towers. The tallest 269 meters high. The 20,000-ton steel bridge deck is the length of 5 Titanics. It's so high, one World Trade Center in New York could fit underneath. The deck is attached to the towers with 400 kilometers of cables, enough to stretch from London to Amsterdam.
There is no other bridge like this in the world.
But to create this unprecedented structure, the team need to solve many tough engineering challenges. how do you construct terrifyingly high concrete towers?
It's very difficult to pump the concrete from the bottom to the top. It's really a critical issue during the construction.
How do you assemble a super long bridge deck in such a dangerous environment?
The valleys here are so deep you can't even see the bottom. This is too high to build temporary scaffolding for a bridge deck.
But the biggest problem of all, what type of bridge do you build on vertical cliffs full of hidden caves and crumbling rock?
To build a bridge here is really a great challenge for me. I'm not sure we can achieve or not.
More trucks.
Visiting architect Wendy Fock is exploring the deep valley.
The rocks around this region are very soft. Also, it's very steep. To make things even more difficult, there are a lot of hidden caves and cracks along the mountain. This poses a huge challenge for the engineers to design the bridge.
The problem is that most types of long span bridges need support anchors built into the rocks. For an arch bridge, weight pushes down and the bridge's curved shape moves the force sideways. So they need gigantic anchors in the banks. On a suspension bridge, the deck hangs from 2 cables, which also need huge anchors to stop the bridge collapsing. But the soft, crumbly, landslide-prone rock in this region isn't suitable to hold massive bridge anchors. It's a huge problem for Deputy Chief Engineer Leo Bohr.
This is an example of the difficult geology. The limestone rock, and you can see so many caves and cracks on the rock. This kind of caves is adverse geology to the bridge foundations. That's quite a big issue for the bridge design and construction. It's really a nightmare of the engineer.
The only option is to find a bridge design that doesn't need the support of anchors. So the team have to draw inspiration from the pioneers of the past.
This is amazing. A tour of London on a beautiful sunny morning on a boat on the River Thames.
Physicist Andrew Steele is exploring London from a unique perspective.
Look at this absolutely beautiful structure. It's the iconic Tower Bridge. From down here, this structure just looks absolutely enormous.
There's an astonishing range of bridges in the British capital, which could help inspire the team in China.
This is Blackfriars Bridge. It's an arch bridge that was constructed in 1869, and from underneath you can see these beautiful wrought iron ribs which are holding the whole structure up. Here we have Chelsea Bridge, a suspension bridge. You can see that big red cable running along the top, that's the main cable.
Amongst these famous giants, there's a lesser-known bridge that's actually one of the most important in the world.
This is a piece of engineering history, an entirely new type of bridge that people didn't think at the time could even be constructed.
Built in 1873, this is Albert Bridge.
From an engineering point of view, there is an awful lot going on here. You can see we've got these support columns, we've got the curved cables, the straight cables. It's 216 metres long in total, and the main span is 137 metres. Pretty daring for the time.
Albert Bridge is the brainchild of British engineer Roland Mason Ordish, who was determined to build the impossible.
The Victorians had managed to build loads of different kinds of bridges, but there was one particularly desirable design that remained elusive. It's called the cable-stayed bridge, and the idea actually dates from centuries before. It was in the 1600s that the first cable-stayed designs were proposed, even before the existence of actual cables.
The design of a cable-stayed bridge means all the weight is carried up through the cables and down through the towers. So it doesn't need anchors on the banks. But in the 19th century, building a cable-stayed bridge had never been successful because the forces are so complex.
The problem was the maths was just too hard. Imagine trying to calculate all the forces on one of these cable-stayed bridges. You've got loads of different cables, all at different angles, pulling on the bridge, pulling on each other. It's a trigonometry nightmare.
Overtensioning even a single cable could lead to a catastrophic failure of the bridge.
For 200 years, people thought the cable-stayed bridge was never going to be built.
Ordish knew the risks of building a cable-stayed bridge. So to ensure Albert Bridge didn't fail, he ingeniously combined it with a suspension bridge.
From up here, you can really see what's going on with this bridge. Since we're in the middle, this is the main cable, the suspension bridge aspect of this structure. And we've then got these smaller suspenders. And what these do is connect the main cable to the span of the bridge, allowing it to support the bridge at multiple points along its length. And then finally, this is what makes this bridge so special. Here we find the cable stays, and it's really clear from this angle what they do. They're taking some of the load from this span and then transferring the force up into those towers there. This is two bridges in one, and that is the genius of Ordish's revolutionary design.
Albert Bridge was a major step towards building a pure cable-stayed bridge that didn't need anchors. Exactly what the engineers in China are looking for.
Ordish's success with this structure allowed engineers to look on this design with fresh eyes, and suddenly what was formerly impossible seemed within reach.
Today, cable-stayed bridges are commonplace.
So when you see a modern cable-stayed bridge, it's all thanks to pioneers like Ordish, who, over 150 years ago, showed that this elegant and deceptively complex design could be done.
In China, engineers have built on Ordish's groundbreaking work, supersizing it for the 21st century. Creating the first cable-stay crossing to ever hold the title of world's highest bridge. Wendy has special access to this engineering marvel.
This bridge is amazing. This is so exciting. I'm gonna actually go and climb over this and take a closer look at the cable stay myself. The view up here is absolutely insane. It's actually quite amazing that this bridge is held up by the cables and by these amazing towers that are on the left and the right of us. So there are no anchors on this bridge. The only way to build this bridge in this region is to have a cable stay design.
The load from the 20,000-ton deck and everything on it is carried through 224 cables into the towers and down into the foundations, removing the need for anchors. But attaching each cable was an extensive job for engineers.
There's actually a lot of smaller cables on the inside that's bundled up, that is then connected onto the anchor point on the bottom.
First, one of the cable strands is pushed through a waterproof casing. It's then attached to one of the towers and joined to the bridge deck. More strands are then threaded through the casing. Up to 43 make up one cable bundle, the longest of which is 382 meters. Each bundle is tightened to a carefully calculated strain.
Getting the cables and the tension right in this bridge is crucial. So inside of each of these cables is a gauge that measures the constant tension on this bridge.
If any of the strand cables fail, engineers in a control center can spot it straight away and replace it.
The marvelous aspect about this bridge is that even if you were to remove one cable, the bridge is still stable. And that's pretty incredible.
But winter in Guizhou brings a whole new set of problems. It's one of the most severely frozen areas in western China. And because of the bridge's altitude, ice could form on the cables. It's a potentially lethal problem that Liu Bo and his team must solve.
If the ice spreading comes, there will be some problems related to the safety of the traffic.
So the ice will cover the cable in winter?
Yeah, the ice will accumulate. Most bridge propose the cables in the middle, just above the carriageway.
Yes.
When the ice accumulate on the cables, there will be ice fragment falling down onto the deck.
With the risk of falling ice causing a potentially fatal traffic accident, engineers came up with a brilliantly simple solution.
For this bridge, we propose the cables out of the carriageway on the edge of the deck, then ice drops out of the carriageway.
That's very clever.
Yeah.
Moving the cables to the edges of the bridge forces ice to fall safely into the valley, helping to keep this vital lifeline flowing all winter long. Soaring over half a kilometre, the Beipanjiang First Bridge is higher than any other on the planet. At 1.3 kilometres long, it's engineering on a massive scale.
This bridge is incredibly long, and it's really rare for a cable-stay bridge to be this long.
Devising a super long cable-stayed bridge is extremely complex. Everything is connected. If one thing changes, everything else is affected too.
Imagine my hands are the cables, and as the span of the bridge gets longer, the angle of the cables get flatter, and that's bad because it puts the deck under compression. There's an optimal angle for these cables, which are 30 to 40 degrees, and in order to build a bridge this long, you need a very tall tower. Basically, the longer the bridge, the taller the tower.
This exceptionally long bridge needs exceptionally high towers, throwing up a further problem.
In order to build the tower, the engineers have to think about getting concrete all the way up to the top. It's just mind-boggling.
So how do you build soaring concrete towers? The answer lies with a pioneering innovation from the past.
I'm pretty excited to be here. This is a really special piece of engineering history, and not many people get a chance to come here.
Physicist Susie Shee is in Hampshire in the south of England.
Thank goodness I invented lifts, huh? It's 330 steps. I don't even think I'm halfway.
She's getting an exclusive look at a little-known but vital piece of engineering history.
In the 1860s and 70s, there was a huge fascination with building stuff with concrete. People would build sculptures and other objects, but no one had yet dared to build something as audacious as a tower out of concrete. They all thought it would collapse under its own weight.
But one man was determined to prove everyone wrong.
Aha! Finally made it to the top.
This is Sway Tower.
Oh, wow. What a view.
Standing over 66 meters high. When it was built in 1885, it was the tallest concrete structure in the world.
I can see the whole forest, and I can see the sea. It's incredible. You can just see for miles in every direction, framed by these beautiful, beautiful windows. Definitely worth the climb.
Sway Tower was built by Andrew Peterson, a retired High Court judge with a passion for architecture.
What's incredible is that all of this was built by Peterson, who was just an amateur enthusiast, and yet he made this huge impact in civil engineering.
Just like the engineers at the Beipanjiang Bridge in China, Peterson needed a way to build his tall concrete tower. The ingenious method he came up with would change the world.
So how do you make a concrete tower? Well, obviously concrete, and a mould to form it in, and the concrete then gets pressed into the mould. The consistency of concrete in those days would have been pretty thick, like my one. So the next step to build my tower up is to get another mould and keep going. That's looking pretty good, so I'm going to add a third one.
But in the 1800s, the moulds were the most expensive part of building with concrete. Peterson came up with a brilliantly simple solution to use fewer moulds but still build high.
By the time I've poured in the top two moulds, the bottom one has set. So then I can remove the bottom mould and place it back on the top and keep going. And then you could just keep doing this, moving the different moulds up, and the tower would grow floor by floor. And the only limit was how tall you dared to go.
It's called climbing formwork.
Yes, there we go.
And it's still the go-to method for building tall concrete towers.
Oh goodness. There we go. I think if Peterson saw this, he'd think I need a little more practice before I build a real one.
Remarkably, Peterson used just 3 moulds to build this entire concrete tower. It's still the tallest non-reinforced concrete structure in the world.
What's incredible is you can still see the lifts where each of the layers of concrete was poured, and it would have taken 2 days to fill each one and then 2 days to move the bottom one up to the next layer, and it took 6 years to build. You can see the lines here between each layer. Peterson proved the world wrong. He showed us 130 years ago that we could build a tall tower out of concrete. And that paved the way for us using concrete in structures today.
Engineers at the Beipanjiang First Bridge in China are taking Peterson's revolutionary construction method to the next level. Two immense towers. The tallest, 269 meters. They are engineering megastructures in their own right.
This thing is colossal. You can see from top to bottom, it's just so big. They're towering over you so much that you feel very small. This is such an amazing piece of engineering. These towers are just tremendous.
But before these towers could be built, engineers first had to work out how to make more than 120,000 tons of concrete. Zhou Ping, director of the Beipanjiang Bridge, needs to tackle this issue.
To make a bridge, we need tons of concrete. To make concrete, we need lots of sand. But you can see, around here, there is no natural sand. It's a huge problem.
The answer was to use the difficult environment to their advantage.
To solve the problem, we produce millions of tons man-made sand. Just like this, we make it by crushing and grinding rocks into small pieces.
Not only is crushing the soft rock to make sand an ingenious idea, but it has an added benefit.
We can control the size of the man-made sand to make different strengths of the concrete.
Finally, construction of the towers can start. thousands of steel bars are formed into a grid to reinforce the concrete once it's poured. Just like at Sway Tower, climbing formwork is the key to raising these super towers.
In order to build the tower, the engineers had to design a mold. And then they added concrete into the mold and then lifted it up manually so that they went up section by section.
Assembling the molds manually enables precise control, so engineers can form the demanding H-shaped design. As the towers grow, so does the challenge. Initially, concrete is lifted in enormous vats by huge tower cranes. But at greater heights, a pump is needed.
Man-made sand is a little bit rougher than natural sand, so it is difficult to pump up to the top of the tower. So we have to use a great pressure pump to pump it up.
A high-powered, gravity-defying pump is used to propel the thick concrete to a height of almost 270 meters.
These towers seem to be going on forever. You can't even see the top of it. It is quite amazing here.
When they topped out, 46,000 cubic meters of concrete had been used to make this pair of colossal towers that soar over the landscape.
And you can still see the lines that are left behind from the mold all the way to the top, and that's pretty cool. And it's pretty amazing to see like the inside of this tower. You could even hear the echo in there.
These exceptionally tall towers ensure the cables are at the optimum angle to take the weight of the massive bridge deck.
Because the bridge needs to be so long, these towers need to be so high, and the engineers definitely did that.
Engineers must now face the most dangerous phase of the project, constructing the bridge deck.
It's a gorgeous view, super deep.
New York-based architect Wendy Fock is testing her head for heights.
It's about 565 meters deep. It's so difficult to even see to the bottom of this valley. It's impossible to build a scaffolding to reach up here, to build a bridge deck. So the engineers had to find another way.
Without scaffolding, how do you support the 1.3 kilometer long bridge deck whilst it's being built? It's a problem that might prove impossible without the innovators of the past. Engineer Luke Bisbee is at the Firth of Forth River near Edinburgh in Scotland to see a piece of engineering that could prove vital to the team in China.
In the early 1800s, engineers were in a desperate race to build a rail line between London and Aberdeen along the shortest route. And this meant building a track along the east coast of Scotland. But this huge estuary, the Firth of Forth, was standing in the way and presented a major obstacle. Building a railway bridge here seemed like an impossible task.
The typical method of building bridges at the time was to use temporary scaffolding to hold up the span whilst it was constructed. Once complete, the scaffolding was removed, leaving the finished bridge.
Here, it's completely impractical to build a bridge with a scaffold. Not only is the estuary very wide, but it's also very deep. And even if you could get your scaffolding poles down that far, the bottom is completely full of mud and silt, and so they wouldn't hold. Here, it would take an incredibly bold engineer to build the bridge, without a scaffold, and of the enormous span lengths required, which had never been attempted before.
British engineer Benjamin Baker risked his reputation when he took on this impossible challenge.
I really can't believe I get to do this. Normally, only engineers who work here get to be here. Morning.
Come on, man.
Baker's solution is one of the most astonishing pieces of Victorian engineering anywhere in the world.
Now this is just incredible.
This is the fourth bridge.
Now that is a view.
A 2.5-kilometre long cantilever design. The longest bridge in the world when it was built.
That is amazing. Engineer's bucket list, this one.
But constructing such a long bridge here would not be easy. However, Baker had a brainwave that might help the engineers at the Beipanjiang first bridge.
Cantilever bridges are all about balance, with the weight of the steelwork on one side of the tower balanced out by the steelwork on the other. Baker also used that counterbalancing act to construct the bridge. The towers were constructed first, and then the bridge was built out symmetrically on either side. Every time a beam was added to one side of the bridge, an identical beam was added to the other side of the bridge. And in this way, the bridge became the scaffolding for its own construction, and it seemed to defy gravity.
It was an incredible solution, and Baker's risk paid off. The fourth bridge opened in 1890. It now carries 200 trains a day and 3 million passengers a year.
130 years ago, Baker's ingenious balancing act changed the way that bridges are constructed. Engineers were no longer reliant on scaffolding beneath bridges during their construction. Provided the bridges were balanced about their central towers, they could be constructed to almost any length, regardless of what was or wasn't beneath them.
At the Beipanjiang first bridge in China, engineers have taken Baker's simple yet brilliant idea to jaw-dropping new heights. Like the fourth bridge, they've constructed the deck without scaffolding by balancing it around the towers using cables.
In order to build a bridge without temporary scaffolding, let me show you what they did here. The approach span was already here, so in order to add a new section over the gap, I'm adding a cable to hold it up. To keep the forces balanced, I now need to add a cable on the other side of the tower.
Adding the cables symmetrically keeps the forces around the towers balanced and supports the deck.
And now I'm adding another section over the gap. And every time I do so, I have to add a cable to hold it up. And another one on the other side of the tower to keep it balanced. I add another section, I add another cable in the front, and I add another one in the back. And there you go, a perfectly built cable stay bridge.
During construction, instead of building beam by beam over the deadly drop, the main span is built in sections. Then, in a world first, the deck sections are slid underneath the growing span. They're lifted into place then fixed to the end of the deck. Construction was twice as fast compared with traditional beam-by-beam building. After only 42 months, for the first time ever, the two sides of this vast valley were joined.
Seems like I'm walking forever on this bridge. Can't believe how long this bridge is. What an amazing piece of engineering.
But before traffic could cross the massive 720-metre main span, Deputy Chief Engineer Liu Bo had one last problem to solve.
There are so many highway trucks in this region. When we design our bridge, we need to consider the loadings of highway truck. Yes, you know, this kind of highway trucks, yes. is very heavy. The stiffness is very important for the bridge safety, especially for such long span bridge.
When heavy vehicles cross the bridge, if it's not stiff enough, the deck could sag. If this happens repeatedly, it will cause fatigue, which changes the metal, making it very brittle, risking a sudden collapse. Stopping this huge deck from flexing is a serious challenge. The solution? An orthotropic deck.
Let me show you how the orthotropic deck works. We select two pieces of flat cut, and we make a bridge here, and then we put some weight on it. Wow, straight away, collapse.
The card isn't stiff enough.
So next, I will make an orthotropic deck.
It's still using the two pieces of card, but this time the bottom one will be shaped differently.
I'm folding the card into box shape. It's just like the U-beam of the orthotropic deck. We can see what happened of the stiffness. A new bridge here, and we put the same weight on it. Oh, still working. Excellent. Just by changing the shape of one of these card, we can make it much stiffer.
Now the bridge is stiffer, it doesn't flex when it takes heavy loads.
Still working.
Solving the problem of fatigue.
Oh, cannot imagine. Excellent.
The orthotropic deck was installed in 31-ton sections. The finished span is so stiff, it hardly flexes, even in the middle. To see it, Liu Bo is taking his colleagues to an area off-limits to the public, inside the bridge deck itself.
Wow, look at this.
Huh?
Yeah, very amazing.
Yeah. We can see the orthotropic deck above, including the top plate and the U-ribs. We use small ribs so we can provide enough stiffness for the heavy tracks.
The orthotropic deck is the final piece of the puzzle for this world record-breaking bridge.
It's hard for me to imagine how they actually built this thing on this height. I think it's very incredible.
Actually, I'm quite proud of it. We achieved it. It comes true.
It's very beautiful.
Just beautiful.
The Beipanjiang First Bridge is taking engineering to breathtaking new heights.
I can't imagine how this bridge could be built if it weren't for modern day technology.
For the team behind this astonishing project, the achievement is immeasurable.
For me, as a young engineer, I think this bridge is very inspiring.
You know, we really conquer so many challenges from the very beginning stage. It's really impressive.
Spanning the mighty Guizhou Valley, this astonishing bridge is engineering on a legendary scale. Over 1.3 kilometers long, with two landmark towers reaching up to 750 meters above the river, it has 400 kilometers of steel cables to hold up a 20,000-ton deck. It's an epic structure unlike any other. The Beipanjiang First Bridge is cutting-edge engineering on a staggering scale, finally joining two regions that have been separated for centuries.
We're now doing the same journey again, but instead of 5 hours, we're only taking 1 hour across this region. This is an absolutely amazing bridge, just really elegant. The view here is breathtaking.
This bridge changed the local people's life. It is incredible engineering achievement.
Inspired by the pioneers of the past, overcoming terrifying challenges, engineers have pushed forward the boundaries of innovation.
When I look at the bridge, I'm very proud of it. To me, it's more like a child. It's grown up and now it can contribute to the society.
And they've succeeded in making the impossible possible.